Yeah. So we'll wait for a minute or two to give a little more time for audience to come. Ask him to wait. Okay. We are not starting yet. So in any case, I just wanted to let you know. I mean, I posted some of the slides, but not completely up to the last day. But I think the day before yesterday's slides are available. I don't know whether you had time to review general stuff on the papers that I said, particularly on both floods and droughts. You got even from the history of what we did through all the way up to using visualization tools, using GEE, or in drought modeling using some of these machine learning algorithms, MLP, multi-layer perceptron approach. I don't know whether you saw those papers. So there is a chronology of papers that we have, starting from basic flood modeling work, integrating hydrology, hydraulics, climate change models, to all the way up to machine learning approaches. In the same way for drought also, using soil moisture, field data, using remote sensing, using machine learning algorithms, you can see the genesis of how our own research has evolved. It's not me or Dr. Venkat Reddy. It's all the students, the research scholars and postdoctoral researchers in our group. Quite a bit of effort they put in to get to this point. Again, science is always advancing, so which we are going to talk about, like what are the gaps we have still. It is not that we have reached a point where we have figured out everything, where we have understood all the things. It is not like that. So it is still developing, and there is plenty of room to really do a lot of good things. And I'll also show some videos on sustainability and adaptation, especially coming from Delhi Center for Science and Environment, Dr. Sunita Narayan. I think she is doing a wonderful job in providing the overview of the crisis and how we can mitigate in India, how we can adapt to those changing conditions. It's not a long video, but depending on the time, we will kind of play some of those things just for our own understanding, so it helps. Whatever I talk, it's a global context related topics, but for you to really take away from here would be connecting those global context to the local issues. So that report or that video, actually those videos that we will see, connects those dots. So that's why I wanted to show without eating too much of time on class time. That is another challenge that we have, but we will do our best. I hope most of you are here, so let's get started. Today's topic is on climate change impacts, risks and adaptation. In the US, it starts there, but then we are also going to extend it to the global scale that I will come back to in a while after this presentation. Basic science that I think we have been talking about in earth systems modeling, coming from our background, mostly remote sensing, civil engineering, hydrology, water resources. We are more interested in soil, vegetation, atmosphere schemes, SWATs or SWATs they call. When used in meteorological models, we call them as land surface parameterizations, which is an important factor, right? So in the first day, if you recall, I said climate of the first kind, and then we talked about climate of the second kind. So now this is the climate of the second kind, but when we are kind of looking at the past, we need to really understand how we evolved, right? So this is the oldest model that they came up with back then in early 20th century. Very simple model they call Budiko's bucket model. So they kind of roughly, the conceptual approach is still the same for dividing partitioning into precipitation into other components. However amount of rainfall that we get, however much rainfall we get, that is divided into runoff, wetting the soil, and also for evaporation. That concept has not changed. but you can see the approach here they are taking is kind of very basic, looking at linear approximation for depletion of soil moisture, or taking the runoff simply like turning on and off the switch for precipitation to ET and runoff. But if you recall the plant that I showed, even to go into that canopy level details, this was not anywhere close to that, right? Then in the 60s, that was in the 30s, right? So now we are talking about 60s, 1960s, way before our time, where they appreciated the feedback what we saw one time. Lack of rainfall leads to lack of vegetation, leads to higher albedo, barren soil, and then that has a reduced radiation, which also creates some kind of a drier atmosphere, which leads to lack of rainfall. This loop that we have is a reinforcing positive feedback loop that we say less rainfall means it's going to get more and more less rainfall. The more the heat is going to prevail, the less rainfall that you will have. That cycle that you are going to see, and that was appreciated in 2 or 3 places back in those days. Primarily they learned this in sub-Saharan Africa, and also they extended this to other parts in China and also in North America. But again, that is not complete, right? In the 70s they came up with second generation 1D models. 1D basically looking at all the atmospheric variables drive the land surface processes, but you can see a little bit of sophistication now they are introducing. Land surface they are bringing vegetation, dividing them, and then dividing the runoff into multiple layers, but still they let the water, deep water, to go into the aquifers. So there is some improvement from the previous generation, but it is not completely developed. So then the lack of that led to third generation SWATs or SWATs, where you see the difference of mixed vegetation by grid. By dividing the grid into fractions, they were able to discretize or give the spatial variability more or less like what you see on the ground. And then they were also giving fractional precipitation. In some parts of the grid you will have precipitation, some parts you will not have. So they appreciated those changes within the grid, so they considered that in the model. And then they considered also the topography, because which is very important for hydrologists, as you can imagine. Water flows through the slopes, so they needed to consider that. So it was an improvement. In the last generation so far, they did not include carbon dioxide exchange in the atmosphere, to and fro, from atmosphere to the surface, surface to the atmosphere. And as you can imagine, CO2 enriches vegetation biomass, right, because they help to grow better. So that feedback cycle was not included until this generation of climate models or SWATs. So now they have included fourth generation climate model, or fourth generation soil vegetation atmosphere transfer schemes. So it includes most of the components that we have seen, but again, when they included carbon dioxide or nitrogen cycle in the atmosphere, it still had some holes. Again, they missed groundwater, assuming that it's computationally demanding or whatnot. The processes were not integrated. But now in the fifth generation, which is what we are probably more or less close to using in all these models, that what we have, whether it is WIC model or SWAT model or any other models, large scale models I am talking about, which includes these feedbacks between atmosphere and land, considers very explicit vegetation, precipitation, and also integrating satellite data for data assimilation. That's an advancement. So, and then it also then considers topography and groundwater. So kind of comprehensive. This is the limit that we have pushed, probably up to 2010 or so. But again, we are exponentially growing with respect to the availability of data, the availability of computational power. So we are able to even increase the resolution that we can run this model. And then now next generation of artificial intelligence driven models have come. So again, using physically based model with machine learning makes it even more advanced for our analysis. So we know, of course, 2/3 of the Earth's surface is covered with oceans. INCOIS gave us a very insightful thinking about how important they are, the oceans are in controlling atmospheric circulation. The remaining 1/3 of the Earth's surface is continents, mostly land mass, and the interaction between land and the overlaying atmosphere is also substantially influencing this whole system, coupled land ocean atmosphere system. Basically, it's a full integration of all these processes that are exchanging the fluxes, mass and momentum on a very regular basis. But when we talk about land atmospheric interactions, the influence of existing land atmospheric interactions that we already saw, but there is also transient changes in land surfaces. For example, I think I may not have shown you sub-Saharan Africa, you saw, right? So on the edges now they are worried that the desert is expanding. So some of the countries are below those Saharan Africa are getting more and more dust storms, sandstorms are moving downside. So the desertification process is expanding. So what they are talking about is now under those transient conditions how the atmosphere and land will interact, and then influence of imposed persistent changes in land cover. Now we know anthropogenic induced changes on the landscape, urban areas, built up areas are changing. How are they impacting the atmosphere is not fully understood. So there are some urban heat island kind of studies that are being done in patch scales, in limited scales, but it's not really comprehensive enough to understand. So this part of the research is actually still evolving, as you can see. Again, land atmospheric interaction, when we talk about, the recommendations are something like using sophisticated data and models are important, but again the process refinement is very, very important. For example, areas of precipitation recycling with a greater realism and accuracy when modeling land surface evaporation. Evaporation modeling is the most important one, because 70% of your precipitation is taken by evaporation, but by no means we are anywhere close to getting that number correct on a global scale. So that's definitely an important thing to understand. Every region, how they recycle precipitation is different. So if you are able to really capture that mechanism for area that you are interested in, that is a good area of research. And then improved understanding of soil moisture feedback mechanism. I think we talked about the loops, positive and negative feedback loops on soil moisture in one class, but again we are not anywhere close, because we are talking about the feedbacks with limited understanding on the soil depth information that we have. Geology is not fully understood. How moisture is held by these the atmosphere, or how they are sucked up by the atmospheric conditions, they are all not fully evolved. So that's an area that I would say still a place to do research. Research is required to fully validate these interactive vegetation models, perhaps using remote sensing data. When I say interactive vegetation models, some models grow crops or vegetation within them. So because of CO2 fertilization, because of increased temperature, because of increased precipitation in some cases due to climate change, these vegetations grow on a regular basis, right? So if you freeze those vegetation growth in your model, you are not really representing a realistic model for capturing evapotranspiration. So now they are letting these crops to grow, vegetation to grow within these models on a daily basis or weekly basis. They change LAI in one case, but then they also increase the height of the canopy or the canopy interception percentage, and how they are interacting with the atmosphere. All of those things are really advancing, especially with remote sensing, but they are not complete yet. Further research is also needed for the area average behavior of heterogeneous frozen precipitation cover, because modeling of that is influencing meteorological feedbacks and hydrological flows, which is also remaining to be very elusive. What is frozen precipitation? Anybody knows? It's not liquid rainfall that we get here in tropics. It's not snow or ice. I mean, it's not snowfall. It's in between. The atmosphere is warm, so it produces liquid rain. Certain depth it will fall as snow, and then there is a layer that changes, the atmospheric layer. Temperature changes suddenly to be cooler than the layer above. You have seen the stable and unstable atmosphere. Sometimes that happens in the atmosphere. Upper layers are warmer, near the surface it could be cooler. So the falling snow suddenly, or it becomes liquid, right? So that falls. The other way also can happen. The upper part can be cooler, the surface could be warmer, and when the other way around, what? The upper surface, when it's cooler, snow falls and it becomes melting rain when it reaches the surface. Also, the liquid rain, when it falls on the near surface, when it's colder, it tends to become little bit thicker and icy. It's very messy type of rainfall. If you happen to be in northern hemisphere during those transition times, you will see the cars are fully coated with this kind of frozen rainfall. It will not melt. You have to keep running the car in high heat for some time before even you can see the frozen rain melting to even clear the windshield. So that kind of modeling has not perfected, of understanding how this frozen precipitation over a large area is changing because of changes in the thermodynamics of the atmosphere that we are still figuring out. And also research is needed to resolve uncertainty in the nature of and to reduce numerical variability of magnitude of predicted changes with large scale changes in the land cover. We are changing the land cover. We all agree to that. Yesterday when you saw the flooded area map with the changed land cover conditions, of course you didn't see pre and post flood land cover to identify what areas were having vegetation and how those changes in the land cover or precipitation has inundated those areas. But if you look at 50-year change between 1970 to 2025, 55 years, you see substantial change over subcontinental India or many other regions around the world. How they are influencing the atmosphere is not fully understood. I'm sorry. So the last part, again, those creating mesoscale circulations, how they can really interact. You remember I talked about jet streams always flowing above, how these land atmospheric interaction can even elevate the rising temperature all the way up to that jet stream level, and what kind of feedback that we have from the land. It can be very, very interesting topic to pursue, but again only limited progress has been made. And again, I'm not talking about the work I did in one place in Nebraska, where the talk of jet stream that is coming all the way to the surface and drying up the whole area, creating large drought conditions in some 1,000 years ago. That happened. The whole area became desert. So we studied that. So that kind of research is needed to understand for current conditions, and then quantification modeling of topography on weather, and climate is very, very important at shorter time scales. We know what's happening generally, like orographic precipitation, how it happens, how these taller mountains are changing the weather and climate over a large area, but we have not perfected at a shorter time steps, particularly how quickly they are changing. That needs to be understood. And again, this graph or schematic that I showed you before, so now you appreciate many of those things that we touched in the last 10 days, and especially with our Incois visit, you could still appreciate all these ocean related thing here in this graphics to what we saw there, ocean heat content is the one that we heard about significantly during our time there, but that ocean heat content in the system is actually impacting a lot of other changes on the landmass is the one that we are considering. But again, revisiting this talk about how naturally varying processes like the solar storms or volcanoes disrupting the emissions or the radiative forcings in the atmosphere, temperature increase that you see on the top, which is also kind of I'm trying to see here if I can, one second. I think it's not working. Maybe I'll give some time. So on the top right, you see the increasing temperature with all the natural variability that we introduced because of some of these disruptions. But then the second one includes man-made changes, anthropogenic changes that includes aerosol emissions into the atmosphere to the land cover change, how they are really adding up to the changes. Only when you add this natural variability on the top plus the second one human induced changes, then your graph matches the hockey stick temperature rise over time of last 150 years or so, that is captured well only when you include both natural and human induced changes, right. So that we have understood. So I think it's working. Thank you. So this graph that I am talking about is the summation of these two. So you can see that the rise in temperature is understood only when you include what we cause to this landscape. I mean, this description again explains what I am talking about. I am trying to revisit this part, which is very important on a global scale. Oceans are playing a big role, and how the heat content and how the density difference is kind of increasing the sea level rise from 0 to all the way up to worst case scenario of 2.1 meters, which is about 6 to 7 feet of water that we are going to have. So you can clearly see the coastal cities are going to be vulnerable. I will show you some other maps on how they are considering the sea level rise to think about developing the areas. How is it caused? Because of the melting glaciers, but again it's a very interesting graphic that I wanted to show you, but I am not sure whether it will play here because some of these things are removed recently from our government site. Let us see if I am lucky enough to see. It's all gone. Data is removed. So we cannot really have that to be shown. So this is the status of climate change research right now with respect to availability of data. So this is really telling you the expansion and shrinking of this Arctic ice over the last what 20 years or 25 years or more. So that is very interesting. From 1979 through 2016, they have shown a steady decline in the aerial extent of this sea ice that is contributing to the melt, which we saw before. And we now know, of course, that is impacting the seas, that is also impacting the inland areas, both quantity and quality, for really understanding how we can manage those changes, right. It's very important. Precipitation, temperature, reiterating what I said before, are causing droughts and heavy downpours. Rain to snow ratios are also decreasing, or snow to rain ratios are decreasing, leading to significant difference between what is available and for as a supply and how it can be used for the demand side. So this is for North America, right? But again, in our case, generally speaking, in the context of India, water supply and demand scenarios are substantially altered already. We are letting about 60-70% of water to go to these oceans, both Bay of Bengal and Arabian Sea on either side, and there is less management. I would say on the management side of water resources, it's more of mismanagement than management, because if we save it, probably you don't need to go through the droughts, but we don't have opportunity to save because there are not too many infrastructure in place. So that is the scenario that you would see. Instead of this reduce the ratio of snow to rain in the North American region. Groundwater depletion, we are going to see as of this year. Again, I am saying for Telangana region, because we are experiencing drought, people are going to suck more water from groundwater, and that's going to intensify drought, both surface drought, groundwater drought also. Water temperature is increasing, which is a water quality concern for us, and of course, frequency of high intensity rainfall events bring lot of pollutants. Like yesterday somebody forwarded, I think Imran, right? So the area that are flooded in Hyderabad, I'm hoping, I'm thinking everybody saw those videos. It's fascinating to see, but I don't know, it was a urban drainage issue more than the heavy rainfall. I don't know the intensity or amount of rainfall that we got for that rainfall. Did anybody track that number for Hyderabad yesterday, day before yesterday? Okay, so it's a heavy rainfall, short duration that came and went, right? That is the kind of scenario that you will see more often. So since we paved the area, that exactly the same thing that what we see here on the board that I draw. So this may be the forewarning that we had here in this class that we discussed. This is urban watershed which we saw. This excess amount of rainfall was seen in Amirpet yesterday, right? So the peak really came very fast, and you are saying within 2 hours time it just went away, right? So even roughly I was drawing, you can see here 0, 2, 3 hours. So you are talking about this peak just came and went, right? It's a typical scenario that you will see in the future. People say, oh, it's okay, no problem. People were suffering for 2 hours, but then it went away. So now life resumes. Everybody goes back to normal. Memory goes away. So then only when the next time comes, people try to remember. Mumbai, the same problem year after year, right? They say it comes, yeah, then it will go. Ganges pollution, they say, oh, nature will flush it out in the end of the monsoon, right? So we kind of see that it is a natural process, but not. It can be I mean, we created this condition, right? People need not have to float on the system that you saw yesterday in Amirpet. So I'm saying, just as an example, that how deteriorating infrastructure, particularly in urban areas, are creating problem, particularly for people who are living there, making business. All those shops were flooded. Maybe the water infrastructure it's becoming a big problem in those kinds of places. It's not in one city alone, right? I'm just pulling up that information because it's fresh in our memory, but it happened in Chennai, it happened in Delhi and Kolkata maybe, and other places also. So I'm saying that this is kind of happening. Infrastructure design, operation and financing principles and regulatory standards typically do not account for changing climate. So we are not including design standards. As an engineer, as a scientist, now, reiterating all of this, have we included this in our design? That is the only question that we should be asking. Have they considered, instead of 2-meter diameter pipe for draining the urban systems, like such a heavily built up area like Hyderabad, maybe they just reduce the size of drainage pipe, or they did not even think of what if the scenario will happen. I will show you the US example, how often some of these frequencies are coming. I am sorry, the last point here is the compound extremes, co-occurrence of multiple events, and then the cascade failure. One thing fails and then it knocks down the rest. For example, yesterday's flooding, if it had happened near a substation, it's going to take away the electricity supply for the whole town. which will be under dark and people have to come and fix it. So it, and then same way, same thing with the heat waves also. During those crisis times, power supply fails, and it creates heating or conditions. You then lead to, for example, in some worst case scenarios, during drought times, power failure happens because hydropower produced energy becomes limited, and then that does not make water systems to be purified. Water treatment plants do not work. People are supplied with bottled water, and again one failure actually leads to the other failure, and people ultimately end up with sickness, health issues and things like that. So you can connect. So water management becomes a big deal. Evolving future, considering evolving future, I think we have to prepare every nation in this case. They do not take address risks that change over time. That is the biggest problem. So as engineers and scientists, when you go to the field next time around, or when you get the opportunity to do, this is something that you should ask. If you have seen historic data and design based on that, that's not going to help. That what we had, you probably heard the stationarity and non-stationarity, right? What is the difference between those two terms? What is stationarity in design considerations? They consider fixed data. See, past is the representation of the future. That is a kind of assumption we make. Let's say you draw a hydrograph or a normal distribution to understand the flood peaks, for example. We talked about 30-year data. How can we calculate 100-year return periods, right? So we do distribution analysis, whether it's gamma or extreme value type or normal distribution, take the tails and look at the percentile, go for 100-year return periods for that as an example I'm telling. But when you talk about this development of these histograms or normal distribution or any other types, it is based on the data that we have collected so far. But we have not collected what is going to happen into the future. We know from the model, but we don't have observations to validate them, right? We all have seen that over and over now. But have we used those in our designs? We have not. The reason is they are model produced. So the regulatory people, the people in the government agencies that approve the designs, right, they may not want to take risk of using unreliable data. So that is one reason why they are not using these projected information, and instead they go with the historic information. That is the stationarity consideration in the design principles, right? Stationary, fixed. Non-stationary means you have to see it is changing, we have to accommodate the designs. Instead of 2-year return periods, now we are getting 5-year times. 5-year floods are happening in 2 years' time. 10-year floods are happening in 2 years' time. 20-year return periods are happening in every 2 years. So those kind of numbers are changing, right? What do I mean by that? Like say 100-year flood means it should roughly happen once in 100 years, right? But that's not happening. It comes every other year in Hyderabad, for example, Mumbai or Chennai. So that's what. So that change, if you include, it becomes non-stationary climate that you will consider, which is not done in our case. So that is a problem. And coastal, for example, just in the US alone, it's a $1 trillion coastal property market, and we are seeing even in our own case, many cities, whether it is Chennai or Kolkata, or Kolkata also, but then Mumbai primarily, or west coast of many cities, whether it is Cochin or all the way up to the south, close to Kanyakumari, all the way up to Thiruvananthapuram and Kanyakumari. So all of these areas are going to be subjected to heavy coastal damage. Storm surges will be also happening. It is not, when we talk about compound disasters, when we consider coastal areas, there are 3 things that we have to see. Extreme rainfall coming from the land mass, right? That is number 1. What else that can cause flooding in the coastal cities? the storm surge, these hurricanes and tropical cyclones, they churn the ocean, they kind of create the surge in the sea level or in the water level, and then that water also enters on top of extreme rainfall that we have. The third one is the tides. You have tides always in the river or in the ocean, and that also, because of the churning, it goes above, and that tidal waves come in. So these three things, when they come together all at once in cities, it completely devastates. It happened in Chennai just 2-3 years ago, right? So people saw churning ocean bringing water from the sea. At the same time, people wanted to drain the water from the city. That water did not get into the sea because that sea was so high that it was pushing it back. That's called compound flooding. This happens in many places around the world, including the US. And yeah, see, drainage is not happening. That's why that land surface runoff is coming to the sea. Everything mixed up, river, wastewater treatment plants, urban sewers, all of them mixing up and showing up in the ocean. But ocean could not take it, because ocean itself is rising because of this surge of waves and tidal waves and storm surges. They are pushing the water back. So there is a kind of a clash between these two systems that's happening right at the border. So we are creating such a mess in those places. Sea level rise is the primary reason for all that, and surface runoff, increased pavements and impervious areas that we are talking about in cities are adding more woes, more problems. Is that the question that you asked, or anything else? Okay. Again, I think everything is affected: fisheries, tourism, human health, public safety, depending on these coastal ecosystems. And sea level rise and higher number of extreme weather events are combined, causing problems. It's not just water quantity alone now. We are talking about both water quantity and quality. Restoring, conserving coastal ecosystems and adapting to natural and nature-based infrastructure builds resilience, ecosystem resilience to climate change, and that's important. When I'm talking about nature-based solutions, I know some of you might be thinking what it is, but I will come to that point little later. Basically, we are talking about protecting the communities and infrastructure through the means of some measure that we take on the ground using natural methods that previously our own ancestors have done, in some cases before all the development happened. The other important issue is there are social inequities, right? So we are looking at the places where flooding is happening. Predominantly, people are also poor. They are coastal communities that live on the huts, in the huts, and then in living in the most vulnerable areas, and they are the most affected people than the wealthy people who are probably living in high-rise buildings inside the city or safer places. So the social inequity is also adding additional pressure, not only here but also in many places. Miami is an example where I'm showing here. Whenever there is a storm, I think they are doing this in many cities, including some European cities, but in India, I think in Mumbai, I think they are doing this. Maybe in Chennai also they did during that flood, like 2-3 years ago that I was talking about. So what they do, since there is that clash that I was talking about due to compound flooding, they use big pumps to come and suck the water, put it in the ocean somewhere else. So for a quick drainage, fix, it's a quick fix problem, and they do this, and it's not sustainable, right, in the long term. A long-term sustainability solution is something like nature-based. In case of marshlands or coastal wetlands, if you create, they are sponges. They are absorbing. These are called, when you develop a city with these measures like wetlands or some conditions like barrier islands, if you create, and then beaches with some vegetation, corals that you don't let go, you save them, making sure of that, and oyster reefs, then finally dunes that you can come up with, protects the city. protects the coastal areas. These are nature based solutions. It was existing before, but because of our development, our hunger for development, we gobbled up all these areas. We took away from natural wetlands. Chennai is a typical example where we took all these waterways, blocking the waterways by building structures, by putting structures, tall high rise buildings, and that really blocked the flow into the ocean. And of course, what we are talking about is these nature based solutions of course can be sustainable, can be maintained, but again for every city this sponge conditions that we create is going to be dependent on what is the best for us. The social inequity that I was talking about is this particular definition. The society has limited resources to help individuals and communities adapt to climate change. This happens both for floods as well as drought. So, when we talk about socio-economic conditions, this is exactly what we want to see. We want to bring everybody together, right? There are finite resources available, only limited amount of resource available, but you have to divide them to people equally. So, in this case, if you look at the left one, current conditions and resources, there is a variability, right? So, this kid cannot see what is happening in the ocean on the other side, so right. So, they are kind of, the height is the advantage here. Of course, it is a graphic illustration of how the conditions change, and again you are talking about allocating equally, equal distribution of resources in this case. So, still it does not reach the needy. Some gets the benefit, some do not. This second one got the benefit at least to get to the higher level, but the third one still is below. So, then you are talking about equitable distribution of resources, meaning it is not equal, but who needs more, that kind of condition. If you create, then everybody is on the same page, everybody is on the same level. This is what should happen in the future to make sure that we are protecting the vulnerable communities. And when it comes to floods or droughts, identifying them, who are stressed, how can we rescue, those kinds of things are really, really important. Distribute resources equitably. This is another example, the place where I come from. This is coastal Virginia near Washington DC area, where the city is one of the fortified cities. We have about what, a good number of naval fleets. You probably have seen these big ships where the aircrafts come and land and fly, right? Those are, what is that, aircraft carriers, right? Yeah. So, there are 17 of them here. I do not know whether you can see in this photo here, but they are all parked here, and they are worried about, the defense department is worried about protecting them because of sea level rise. And then this is a very complex water body system here in the city. There are a lot of Kerala type conditions here, whether it is Cochin or other places where you have inland water bodies that come in. Many other coastal cities, probably even in West Bengal, you have similar coastal areas. Andhra Pradesh, you have probably in Tamil Nadu in some places also. Bombay is exactly like this. So, they try to identify what are the places where we have high growth, like serving as economic engines, and we need to consider them, and whether or not we can fight this sea level rise, or whether or not we need to retreat from those areas. So, that is another condition people are talking about. Is that worth putting up the fight with these rising seas, or should we retreat, go backwards, instead of saying that we will fight you, we will surrender, we will go back, like that. So, in some places they are successful, there are people that are moving inland, right, but in some places it is very difficult to move. So, they are constrained. I have a video on that for US conditions. I think it is a little bit of dated video, but if time permits I will show you how people are fighting. They have water level meters at their home. They can even forecast or get the forecast information to their house on a daily basis based on the moon locations and how the tides change. king tide, they call king tide. When it comes, it really comes all the way inside. And then they are also raising, retrofitting their houses. Instead of sitting on the ground, they have raised with pillars and 2 or 3 feet. So when the water comes, it does not really affect their furniture or whatever inside. So this is the kind of mapping. This is non-stationary approach. What I am talking about, people try to really see what areas are to be protected, and the green areas, that what we are talking about is the new urban centers, right? And the neighborhoods of the future, they are making sure identifying them and retrofitting the existing houses. So this is the old area. Virginia is one of the oldest state in the Union, and basically Britishers came from Atlantic this is facing the Atlantic, right? Through Britain, UK, from there they entered here. This was a port city, and lot of business, trade and everything happened, but it was built on a very shallow area. You saw from that Ramappa temple, right? They said they have built the whole temple on a sand foundation just to absorb shock. In the same way here, of course, they wanted to do something, but I think the area itself is sinking, so that's going down, and the land above is also sinking because people are taking groundwater. Groundwater is a cushion for many areas above. If you remove that cushion, it's like, consider it's a sponge, right, with full of water in it. If you squeeze that water from the sponge, the land mass goes down. That's what is happening here. That's what is happening in many places where groundwater is used unwisely. Okay, mitigation is another important topic here. We talked about risks so far, but there are two other terminologies, mitigation and adaptation. Those are coming together. Mitigation related activities are taking place in the US also, you may not believe, but it is happening, like conversion of EVs, more use of EVs and all that. But as an example, solar powered houses, many places, and many renewable energy approaches are being taken. They are all serving to mitigation of emissions that we have from the land mass, right, aimed at reducing the emissions. That is the mitigation part for those who are of course not still familiar with what mitigation means. Mitigation means we are trying to minimize the emission of whatever pollutants into the atmosphere, particularly greenhouse gas. Risks of inaction: if we don't take any action, if we don't have or limited mitigation, or then the adaptation losses are going to be much more, right? They are going to grow. If you don't mitigate, you will say, I have lot of money, I will invest more and more and more to protect the people, let them also still keep burning fossil fuel. That does not work. It's going to increase everything. Still the risks are not going to be gone. So the emissions that we have already put in is going to exist for thousands of years now. The impact on the ecological side, the physical side, is going to be lasting for long, and they are all irreversible. It's going to be having an impact on that. Many climate change impacts associated economic damages, particularly in the US, can be substantially reduced provided they take mitigation actions. Near-term mitigations happened. We did not meet Paris Accord 1.5 degree cap on emission temperature increase, but again US is failing on that side, but India probably is doing a better job as far as the recent report that I saw. But what does it exactly mean? You have to really distribute the development of or minimize the development and improve mitigation approaches based on how the activities are happening, right? This mitigation and adaptation are complex, but there can be benefits to the local people, communities, if you can convince them. Adaptation and mitigation can complement each other, meaning you don't have to wait to adapt until you completely eliminate emissions or completely aim for full mitigation. It is not possible, but they can go hand in hand or complementary. While you do mitigation approaches or strategies, you can also think about complementarity or avoiding I mean, making better adaptation. For example, in the US, if you look at, every state is different, right? If you look at California, which stands out when it comes to GHG caps, to renewable energy use, transportation, related improvement. You all are riding the EV here, right? So that's a kind of adaptation that we are seeing here on campus. The same way, every state in the US have differential investment for mitigation related activities. Differential mitigation related activities that we see for 50 states that we are seeing here. What are we doing in India for each state? We don't know. How many projects are there to mitigate climate change? There may be some statistics available. That is something of interest for communities like us to see how different states within the country is implementing their own strategies for mitigation, right? So at least it gives you some context, thinking about where should we invest money and where should people really talk about. There are some places in the country are developed, some places are not at all developed. Northeast is still with pristine forests, while south or west or central India is depleting the forests. Some places they are increasing the forest cover. So, and then where is more energy spent? Where are we doing coal mining? Where are we talking about renewable energy projects like solar or hydropower or the wind turbines? Do we have wind turbines here? Do we have wind turbines? Where are those projects? Rayalaseema also? Okay. So think about projects where by state where they are really investing money. That will tell you exactly where are we headed. But most cases in India where the pollution is little bit under control, it is still on the side of development, right? It's not really thinking about mitigation as such, but there are some projects. I will not decline that or deny that. Okay, so now based on that, they look at the investment on which sector needs, which will be affected in the future, potential damages, for example, to the labor market. They cannot go out and work under extreme heat conditions. That's happening already in India. If you ask construction people, they will tell you that, between 11 and 3 or 4, they are completely, taken away from these, heat exposures. That reduces the economic activity. So there are damages associated with each of the sectors. For example, in this case, if you look at, the labor market and temperature increase, coastal properties, air quality, Delhi area, for example, if you see, people are not able to function normally during certain number of hours in a day. So how is it affecting the economy now, and also how it will get worse in the future? That quantification needs to be done on a state level and also by sector level to understand where we can put our money. So again, to reiterate this thing, adaptation planning and implementation are occurring in many parts of the world, including the US. Implementation has increased, but it is not completely taking over the places, all the places. Successful adaptation is hindered by the assumption that climate conditions will be similar to those of the past. That is the stationarity assumption that I am talking about. People are not ready to adapt because they think, it has come and gone, it will be like this, so don't worry about investment for adaptation. And incorporating information on current and future conditions for guiding designs in the future would reduce risk and aversion of impacts to some extent. One thing you have to be clear, adaptation is a constant process. It has no end point, meaning you say, okay, I developed this area, I kind of came up with nature based solution or some kind of a renewable energy project that's going to be helping me to minimize the damage or minimize the risk. No, that is not the way. It is constantly changing. As of today, this is the condition for which you are designing certain things. That means you may have to revise your own adaptation procedures for the future conditions. So because there are lots of uncertainties, you have to keep changing. So it's very difficult And there are of course risks associated by not doing adaptation, but again you have to be proactive in terms of doing these adaptation initiatives, both from the policy side, how you operate the business, what kind of investments you make, right? And then evaluating adaptation strategies involves equity that I talked about before, justice, cultural heritage, environment, health and national security. National security, I said these fleets in one area that I was showing on the map gives you an idea of how they are thinking about retreating or probably understanding what kind of protection they can have. There are new approaches that can really help us reduce the risks. I'll probably go directly to the this part here. So, this is exactly the adaptation procedure that's happening in some parts of the US, but of course, there are still things to fix in this case. Let's look at how they do, what they do here. Even I'll try to break this down. It's a very nice graphic that I like. We need to be creating awareness, right? Which is the first step. What is awareness here? We want to understand the impact. All this class, all these last 9 days, what we are talking about is looking at the risks, looking at what kind of approach or things that are happening around us. We are very well aware of it now. I mean, you are still doing some modeling. When you go back and do, whether it's drought modeling or flood modeling, when you do, you are going to create, you are still being in that circle of creating awareness, right? For that, you will of course be doing some assessments through models, through data, and then maybe interpreting and connecting those two together. And of course, based on that assessment, you will come up with a plan. Okay, what can I plan for addressing what I understood based on my assessment, right? And then try to implement that project. It could be a small project. Let's say drought in Marathwada, I am just giving as an example. Okay, people take water or conserve water as an approach for implementing the project, or converting to drip irrigation, okay, and changing the crop types. Instead of water consuming crops, they probably have water conserving crops. Those are adaptation measures and they implement it on the ground, right? But that does not mean that's over. You have to still assess what kind of improvement that you have made. That's actually called ME, monitoring and evaluation. So, for every project you have to keep doing that. So, start from creating awareness about the problem, assess the problem scientifically with data driven approaches, come up with a plan and design things, and then implement it and assess how they are doing, both from the side of mitigating the risks for people to live there, or economic benefits, what kind of benefits that you reap because of this project. If you do this in a cycle, it really improves. Based on this, I am going to actually show you the video that actually talks about some of the issues, but then after break, I think I will still talk about some of the interesting things on the advancements or lack of advancement in some places, how to look forward, those kind of things that I will still, I am not done with this thing. There are some more slides that I wanted to show, but on a different context, bringing both US and India together on the topics, what they are doing there, how that's useful for people here, or how we can combine the forces, that is a kind of thing. But please bear with me. I'm going to show you this water crisis. I mean, we are interested in water, right? So I will show you water related experience here. It is timely for us to understand because it's India context topic. I will we are probably close to getting a break in the next 10 minutes. I'm going to stop as soon as Dr. Venkat Reddy shows up, okay? And also it gives a break from me talking all the time, and you probably be awake when you hear from somebody else. Let's play this. on different topics. So that's the idea. Is this the link that you have here? Where is it? Oh, okay, okay. MP4. I'll give a primer to that. MP4. Can I play MP4? Download. So, just to give you an idea, we have Mr. Mohan Mane from Nagarjuna Sagar Dam site. He is assistant executive engineer who is doing this dam operations and maintenance kind of work. Central water scheme. This is related to drinking water scheme, that a 3-minute video. You know, in the previous presentation there was a reference to Nagarjuna Sagar Dam and how that is used for supplying water to cities. This particular example talks about how they take water to Hyderabad on a weekly basis, and then you can see the connection to what is referred in that video to how Nagarjuna Sagar. It's a golden opportunity, folks. We are having a person from that project coming here to share this information. So I'm delighted to share this. Thank you for doing this. So it's wonderful to learn little bit about this site, the project that has been already happening in Andhra Pradesh. Oh, okay. When is it? Okay. Oh, yeah, I remember. Another trip. Okay. I don't know. I may not be able to make it, unfortunately. But next time around when I come. But the idea here is, of course, based on this, we will then go to adaptation strategies that I will say. But I think we are still going to come back to research part. What is to be done? What is left? Those kind of questions I want to ask. So through my talk in the next hour. But Dr. Venkat Reddy will join around 11:50. So we have time. Oh, 2-meter diameter pipes that is actually connected directly from the dam site all the way to Hyderabad. So that is carrying water, a quantity of 2 TMC per week. Did they use drones? Very nice. Irrigation. But they send it to treatment plants before they use it for drinking, right? So this is fresh water taken from Nagarjuna Sagar Dam, which is built on the Krishna River in Andhra Pradesh. So they are conveying water to different areas. Of course, in one place where you saw, they were taking water directly from the canal to Hyderabad through piped canals or piped systems, 2-meter diameter pipes. They are huge. So again, you see, there is no life without water, right? So that's the example of how important water is. So we are in a very important discipline here to contribute to. So that's one thing that I wanted to reiterate. So when it comes to adaptation, this is a cycle that we talked about in the previous session, right? So this has to happen on a regular basis for every location, for every type of utility. So it's very important. That way, you know the risks associated with the disasters and how we can mitigate the risks. Okay. The new developments that happens are many in many fronts, as you can imagine. This is a ever evolving situation, right? As such, if you look at the development of climate modeling alone, think about it. You know, we are talking about AR 5 now, 5th generation climate model results with all the socio-economic scenarios that we talked about, but there were previous scenarios. There were improvements that were constantly made, right, from 3rd generation to 4th generation, 5th generation now. So this has improved the fidelity of both the models, model outputs, and then use of them for making decisions. But we are not still anywhere close to coming to a scale where we can really operate the climate model at a scale where the action is taking place. That is a gap that we have in research. What do I mean by that? Let's say you have developed area like Warangal, right? When you kind of put this in a box, right now in climate model, it has urban areas, it has neighboring areas that may be forested or agriculture or barren lands. So it's kind of massaging or kind of morphing all of these things together in the model. But the next generation climate models, of course, are looking at even dividing this at the patch scale level and running this model for each processes where things can be quickly quantified. That is how basically the development has happened from CMIP generation of models. Now we are talking about CMIP 6. So impact, again in that adaptation circle that I talked about, we are still trying to understand creating part of awareness, right? That is in the first segment. But there are significant differences between or points of opinion between climate modelers and observing people, the people who collect the data. But that collaboration has really improved a lot because they realized, each party is needed to make improvements with models, improvement in prediction or improvement in observation, how to collect the data and all. So that is one thing certainly has happened. And understanding of anthropogenic induced changes. So far people denied that, oh, humans were not responsible. Not so far, at least 5-10 years ago, they were realizing, they were convinced that it's not humans causing the climate change, but that is now behind us. People are causing problems. That is established, but it is not still fully established in terms of how each of the events are contributed or the reason from the humans. That kind of linkages have not been established. Improvements have happened with respect to models, including resolution that I talked about, and updating the process. For example, as we go, they realize, wow, yeah, this equation is not really capturing what I want at the canopy level, or this equation is not really improving my cloud physics part. So then they try to modify that in the model and improve it. So it's been happening because we have now data and also computing power. Powerful computers, GPUs and supercomputers are useful. So again, model developments cannot happen in isolation. This has to be along with observations and especially high resolution information, both from in situ on the ground plus satellite data, right. So that's the advancement that's happening. And then we also have to have sufficient length of record to assess the skill of early projections and track advances in understanding. You know, early 1990s, when climate model outputs IPCC, you know, from 1988 all the way, if you think about first generation, you know, like I talked about before, IPCC came into existence in the 90s to all the way till now. You know, over the past, they were trying to go back and say, what did we say in our first report? Is it happening now, 32, 35 years after? And for the most part, yes, they said temperature will increase, and you see that hockey stick has proven to be increasing. They are right, you know, even with minimal data, minimal information at that time relative to now, they were able to do that kind of forecast. So that's the kind of you know, achievement to, you know, science, right. We also talked about these graphics, if you recall, of course, you know, shrinking Arctic ice or snow cover sea ice extent, or the feedbacks. So with respect to clouds, or with respect to land atmospheric interaction, or ocean land atmosphere interaction combined. So they are pretty much, when you combine all of these processes in the model, combining all of these things provides very close correlation to observed changes. Again, it's a very impressive feat in terms of achieving the evolution from the first to fifth AR and now sixth also. Ice sheets models, for instance, have the capacity to explicitly simulate dynamical imbalances, and also projections of sea level rise contributions are very close to agreeing with the observations. You know, what they said was, you know, you will see an increase of 3 millimeters or so per year, and over the years, I think that has substantially increased also, and the model, it's an exponential growth that we have seen now. So again, that's proven to be correct, both from the model side by validating with observed data. So until AR5, that is you know, the previous generation climate model results, the cloud feedbacks were not resolved. You saw the complication in one of the video that I showed, right? Low level clouds, high level clouds, how the feedbacks happen, positive versus negative feedbacks, right? You recall that discussion before? So that has been captured in the model now very well. Clouds were the most intriguing entity for modelers, but now that is resolved to some extent. Developments in methane sources and sinks and quantification of agricultural yield impacts offer further evidence of advanced understanding. People did not realize that rice fields are this big source of methane emissions, right, in the past, but now they realize, wow, this is a big chunk of, you know, many more times of, you know, potency with respect to methane compared to carbon dioxide in the atmosphere. So that level of recognition has happened, and they are able to actually identify what are the sources on the ground, what are the sinks are on the ground for these emissions, or CO2, methane, nitrous oxide. So all of those combinations have really improved the model predictions. Again, looking forward, early, you know, successes and continued developments provided, of course, significant you know, shot in the arm or power to climate scientists and modelers like us, saying that, yeah, we can do better. But one thing that we have to remember, you cannot be complacent, we cannot stay idle, we cannot say that we have achieved. that what we wanted to achieve with respect to understanding the climate. It's still a long way to go, because there are some uncertainties with respect to cloud physics that we talked about. Apportionment of methane sources and things still can be improved with observed data. How agricultural crops are contributing to and also impacting the yield part with respect to climate change and how it affects food security, the big picture thing can still be improved. So we cannot stay satisfied as such. So that's a motivation for us to say that okay, we need to still do again, we need to still do more in terms of model validation, process improvement, or how you can capture the inner part of the model workings and all that. Of course, there is a contribution both from modelers and also observationists, and that is very, very important to keep going. There are new models that are available for understanding the physics, impacts and mitigation of potential anthropogenic effects. So now I am showing this Nature Climate Change article where, I mean, it's a little bit of a dated paper, but again if you look at 8 years after, it is still the case. The highlights of this paper talks about the 100-year floods or 200-year 500-year floods that they talked about are not valid anymore, only with the previous records or past records. We need to really think about how the changing conditions are needed to be included when you calculate these return periods. For resilience planning, we need to really have no limitations on using only certain type of data. So these extreme storms and flood events are happening more and more, and they said that 8 years ago. And of course you can see in India, like this is a previously shown slide that I wanted to highlight again to reiterate. When you looked at flood maps yesterday that you plotted, right? So now you can relate. That's the one of the reasons why I show this graph. When you go back, use the skills you learned in terms of even visualizing after every rainfall event, flood events, to see whether or not it gives you an idea of the spatial extent and even the information on how much of the flood depth that you can have. Of course, science is advancing in that regard, but it's not fully developed yet. So people need information about how much water they are going to have in their neighborhood, in their streets, in the areas that they are using. So that will tell how to evacuate, how to help people to be safer. Those kinds of things have not fully happened. There should be a shift in thinking to resilience planning. That is what the resilience for flood and drought studies actually need to look for. They need to shift their thinking. Basically they are talking about built-in infrastructure, and not only they need to consider them, but also people who are residing in those facilities, right? Because it is not just protecting these infrastructure that are already in place, but how to really see who are the users of it, how we can improve, not for today, but 50 years from now, 100 years from now, if you want to really see those places or as it is in terms of safety wise, without all these extreme events impacting them. We need constant thinking and improvement to our modeling approaches. Mitigation can be large, what I said in terms of cost wise, to save the city only in terms of doing mitigation aspects, because mitigation is not local. It has to happen over a large area. Everybody should come to the table, everybody should agree that we will minimize pollution in the atmosphere, we will have more greener conditions on the ground, less emissions, those kinds of things. But that is kind of a large effort, both in terms of cost as well as the capacity. But of course they can still be needed if you invest sufficiently for both mitigation and adaptation. They can kind of combine the effects of climate change and also the extreme events that what we are seeing more often. The papers that I am showing here kind of summarizes some of the nicer things that you can actually read. It's very informative for doing the analysis on seasonality, intensity and duration of rainfall extremes in a warmer climate. So, this is applicable to you also for your study. So, I am just putting it out here to create interest in looking at your data to understand what kind of rainfall regimes that you are seeing based on the data that is available to you. This is the US condition. What they are talking about here, which we already discussed, floods are becoming more common, extreme rainfall statistics is becoming more promotional call, sorry. Thermodynamic properties of air, which we discussed before, the drier air can hold more moisture, 6 times more moisture, and they dump the rainfall in a very short time. You saw from the video also before, they said, you know, seasons worth of rainfall is happening in one day or 1 week. That kind of rainfall event, you know, 3,700 hours or so they were saying, of which only 100 hours you get the whole rainfall. So, that amount of dumping is happening, land surface cannot handle. That you see everywhere, not just in India, but it is also in other parts of the world. One other important standing out fact here, as you can see, I highlighted, these rainfall extremes are changing. 20-year event is now becoming a 7-year event. So, that is very interesting. I mean, if you recall the basic understanding of the return period calculations, it will be 1 inch, I am just giving an example, 1 inch for maybe 5-year event, or 2-year event, and if it is a 20-year event, it may be 3 inches, but 3 inches of rainfall now coming every 7 years. Instead of 1 inch, now 3 inches of rainfall coming every 7 years. So, the frequency of these high magnitude rainfall events, right, high return period rainfall events are happening in a shorter period itself. So, that is a challenge that we have to be facing with. In every parts of the US, I think they are calculating. This paper actually confirms what people have said about how the atmosphere is holding moisture, extra moisture. So, based on theory and models and observations, they are able to establish that fact. It is not just they are showing, based on some arbitrary numbers. So, observation of heavy precipitation, of course, is also important, right, observation of heavy rainfall events, but how can you integrate that into process models and improve the predictions? That is certainly needed. Consistency between different lines of evidence. We are talking about observation based analysis, we are talking about model based, combining them, maybe even within models, model A, B, C, and then talking about physics based, physics guided machine learning model. So, all of those things combined will actually give a wealth of information of how you can take advantage of both observations and models. The water cycle, I think this is a repeat of what I said before, of looking at how we have modified. As you can see from Nagarjuna Sagar, just we recently saw that video, right. We have taken water from one place to move it to another place. How do you account for water budget in your calculations? If you are running the water accounting model, you have to see all these sources or demands and supplies and see how that is going to change, not now, but also into the future. So, example of Nagarjuna Sagar, the study where how inflows will change, how the supply quantity will change in the future. Can they really supply 2 TMC in the future as they are doing today? Will that be sufficient for Hyderabad because of population increase, because of evaporation increase? You have open canals and you have reservoirs built in places to save this water. If they are going to evaporate more quickly, do you think you are going to compensate that with open channel flow or cover it up with something else? We also saw cover and erosion on the sites where there is no vegetation, but plants can suck up more water and they can transpire on the edges, on the borders, but there is more erosion because of heavy rainfall. There is also going to be uncertainty with respect to supply side also. This year, for example, it failed, monsoon failed for this region, right. So, how are we going to operate the dams? So, under those conditions, how this water cycle will change? $1 million question. right? We have a lot better accuracy with respect to improving our understanding on certain things. Okay, confidence in attribution findings are there for greatest extreme, are really greatest for the extreme events, especially with respect to temperature. People can really come up with good predictions on extreme events like heat waves and cold fronts. I think models have really come to terms with predicting them with more precision, more confidence. There is no confidence on convective storms and extratropical cyclones. What do they mean by that? You know, over the Arabian Sea or the Bay of Bengal or Indian Ocean, sea surface temperature is changing. How they are contributing to monsoon systems, how they are contributing to land surface convective storms and also on the ocean, how that climate variability or climate indices, for example, Madden-Julian oscillation that we talked about, or ENSO, El Nino, La Nina combination factor affecting these extreme rainfall events combined with climate change, or Indian Ocean dipole, how it's contributing to cyclonic precipitation, convective storms on the land. We don't know all that. There is no confidence, or there is less confidence in our model predictions. So that happened as of today, as of this year, that what we witnessed based on our site visits, which we can say for sure things are cooking up, something is happening in the atmosphere. So to overcome that, of course, we need more rainfall, right? Are we going to get that in the next cycle or not? We don't know. We are already, from 1800 to 1500 to now 1300, now it's less than 500 millimeters this year. 3 years in a row we already set up drought conditions, but we are not realizing that, right? The onset has already happened. When is it going to break up? We don't know. What will make that cycle to break up? We don't know yet. So it's a $1 million question to answer, right? But the confidence level, if you see low and high on this x-axis, low and high on the y-axis, understanding the effect of climate change for every event. There are many events we talked about. Extreme events, this class is very much tied to this graph if you pay attention to. 7 or 8, on the first day that I talked about, starting from lightning to heat waves to floods, and we didn't include drought in that particular analysis, but then I mentioned that drought should be also included. Cold waves that we had, aerosols, air quality index that we saw, but again these are shorter time scale extreme events, right? If you look at them in this graph, so understanding is actually high, really high, with confidence in capabilities for attribution to anthropogenic change. We are talking about extreme cold or extreme heat with high confidence. We are able to predict, we are able to say for sure we have caused this problem. When the prosperity goes up in India, for example, everybody is going to buy AC. They are going to suck up all the cold air and get nice air conditioning facility. Like here, we are going to emit hot air outside. So when you walk in the streets in the urban areas, you are going to be walking in an oven, hot air balloon, whatever condition that you are going to see. Concrete already paved. On top of that, we are going to keep the houses cool because people can afford to buy all these energy units, and that's going to create more heat, right? But people are actually saying that climate models have improved, our understanding has improved, and humans have caused that change is also understood. Okay, droughts and extreme rainfall, as you can see here in the middle, it's not high, it's not low. Same way, we don't know whether we can attribute those changes in droughts and extreme rainfall events to what we caused because of the other factors that I mentioned before, right? We talked about nature that's actually changing over a time, natural climate variability, and on top of that climate change, sea surface temperature that we are saying, ocean heat content, the fluctuation. You remember that gentleman actually talked about the change within a day is not much, but they can take up all the heat, they can store it they are the reservoirs of heat storage. But again, when they show signs of stress, that can be humongous, because they take long time to heat up, they can take long time to cool down. That cycle, we don't know how long or how less time that is going to happen. That is the reason why we are not able to say why monsoon failed for this year for Telangana, or that is the reason why we cannot say for sure what caused extreme rainfall yesterday in Hyderabad, right. That kind of relationships that you can see, models have not been great. So that means it's an opening for you. You can really, play well in terms of asking right questions and hit a sixer, of finding the answer for that question, and that's an important part. And the other parts, low confidence that you have on other connected events like wildfire, for example. There is some, connection to drought to wildfire, but we have less confidence in drought. And how can we relate that to causing wildfires? There are other factors that play. So complications are there. So pick a particular extreme event here in this scale, for example, and if you contribute to improving the prediction capabilities and attributing that is caused by human beings, if you are able to prove that, that's a big contribution to science. So this graph has lots of wealth of information for us to interpret. So that's what I wanted to say here. So, it's really worth looking at it. When we say anthropogenic induced changes, we know for sure, many factors are there, but for drought, we saw this graphic before, right. So population growth, agricultural development, land use change, urbanization are changing how we even address or cope up with drought. Bringing water in a truck like what we saw in Delhi or in Chennai, they carried water by train one time recently, right. From different parts of the country, water is transferred here, and it came also through the pipes from Krishna river to India, Chennai, right. So flow of water is happening everywhere because of human modifications, and that is causing more problems, particularly with respect to drought, because you remember we talked about meteorological drought with precipitation deficit that's happening this year, which is already leading to agricultural drought to some extent and hydrological drought in many parts, like stream flow, water budget analysis. If you do, you will see stream flow consistently going down. And of course, there is some connection to the drivers of what causes this, but not fully established. So there are some exogenous, that is human induced changes and natural drivers, and endogenous drivers of change that's also happening within the system itself. Okay, so we need to understand that, and they are talking about how a particular lake, in this example from that paper, 98, this lake Urmia in Iran looked like this, it shrank like this, and now in 2015, not even now, it was 10 years ago, how it has changed. And you can see how the withdrawals had happened, what was the lake level here, and we don't know how to operate them, right. At some point, basically, the withdrawals are increasing while the lake level is decreasing, and still, causing drought here significantly. So the demand supply scenario analysis under normal conditions, normal weather climate conditions has not happened. And now the same demand scenario and supply scenario analysis has not, or is not there anywhere close to understanding, full understanding under extreme conditions. Under drought, how do you operate the dams? Under drought, how do you really, keep the supplies coming or minimize the demand? Those kind of questions are not happening anywhere. So that is the part that you need to keep in mind. So many studies are really connected to large scale atmospheric conditions. In some cases where water use continues to increase, impacts on future droughts are also expected to grow. That is for sure we are seeing in many places. Human water use and the local capacity is also increasing because of mismanagement of water resources, and also human demand, the consumption is also more. But what are the gaps that we are seeing? This is particularly related to drought, but I will come to the general topics little later. lack of indicators or comprehensive assessment frameworks for describing anthropogenic droughts. It's a big deal. We have to really link up with the process based models, land atmospheric dynamics, energy balance and other relevant feedback loops are not fully understood. And if you can come up with your own index of drought, I talked about maybe a dozen index, right? Do you all remember a few drought indices that you can name? Maybe random, one by one. PSI, PDSI, SPEI, what else? I mean, talk about precipitation based, evapotranspiration based SPEI he talked about. What about other systems? Anything about groundwater? There was a groundwater drought index GDI or something like that we saw. Base flow index is that groundwater index. What other metrics, groundwater or climate indices you can think of? Soil moisture based, did we talk about that? MSDI, right, or other soil moisture, SMDI that I talked about, multivariate, soil moisture drought index. 2, soil moisture deficit index. What other index I talked about? Coppola based or whatever, yeah, but socio-economic factors, right? We said we are not really reaching that point yet to integrate them. That's probably a big question to ask when it comes to asking questions on anthropogenic impacts on drought and how they propagate. That kind of information we have not still gotten. So 12 or so indices that we listed are primarily based on the systems that we observed, but we are also causing problems, creating stress from one place to the other, moving water from one place to the other. That is actually the human induced changes to the drought conditions. How are we accommodating that in the context of socio-economic drought? That is a question. And then reduced water quality due to anthropogenic footprint. Urbanization, sea level rise, intensive agriculture, irrigation basically and other human activities decreases water quality, right. We talked about non-point source pollution, carrying fertilizers and all other contaminants both into surface water and also into groundwater. Under normal conditions, under extreme rainfall conditions, they wash off all these potential or pollutants into the system, surface and groundwater, and that relationship between water quality both in surface or groundwater with climate change is not fully understood. So if somebody is answering that question, that is a very relevant question to ask, right, through models or through observations, and establishing that it is caused by humans. So one thing that I am trying to emphasize in this research gap is that we are not able to track the human footprint to any of these degrading things that are happening, whether it is in terms of water quality or in terms of drought or in terms of floods or in terms of water quantity. So all of those things are really evolving with respect to attributing that to human activities. The feedbacks are understood, especially on a hotter day. I mean, hot droughts basically are having this negative feedbacks, right. So more drought means more temperature increase will happen. So that kind of feedback is understood, but they can also modify the plant phenology and change the length of the growing season and carbon uptake. We don't know what's going to happen. Plants are very resilient. They can adapt, they can shrink, they can close their stomats, the holes beneath the leaves, right, the stomats that they have. That's how they leak water, that's how they release water vapor as ET. We don't know how they are going to operate under these extreme drought conditions. They themselves will shut down, they themselves will try to minimize the water loss. And how do you model them? How do you physically quantify what is the reduction in ET, or what is the reduction in water consumption by these plants under drought conditions? Are they creating positive or negative feedbacks? You know that, and are we responsible for that? That is a basic question. I mean, plants act on its own, right? But still, because of our activities, are they doing something like that? That is a question to ask. And snow drought, that's not relevant here, that's happening. So in some cases, generally what you have to understand is, we have a 6 month of a winter season, of which about 3 months we get snowfall. If we don't get enough snow during the season, all the mountains that are covered by snow will not have enough snow for melting and allowing water to flow. That's called snow drought, and that is also happening in other places. So now there are science gaps that we talked about, but specifically what can you contribute to? How can we contribute that can be impactful? That is a question I am going to put forward to this class. You can pick pieces of this, and if you do, it can be a PhD thesis, and you can multiply each of these statements. What I am saying here, India, Ethiopia, South Africa, Brazil, or other region of specific extreme event projections. I mean, the example I say was because we had extreme events in all these countries that I was referring to at that time, and that is still valid. It can have more number of countries now. It depends. I am just giving you an example of 3 or 4 countries here. Extreme event projection analysis with CMIP6 type of data set at 4 kilometer resolution is a must. We have to think about using high resolution climate model data. Regardless, however you downscale it, bias correct it, doesn't matter. You know all the skills, you know how to do them. In other sections we talked about it, but whether or not you can implement it meaningfully and make sure that the data is representing correctly, you know, based on comparisons between historic observed to your bias corrected historic data from the climate models at 4 kilometer resolution. If you can do it, it will really important. And then robust validation, observation based analysis is very, very important to understand how can you improve your model. That is my first you know, driver on this part. High resolution flood risk assessment using models, drone LiDAR driven data set for both, you know, channel geomorphology to understanding the terrain, for quantifying the depth of rainfall that you accumulate. Yesterday you had a fancy Google Earth engine based flood inundation map generation, right? But if you have a high resolution LiDAR produced elevation map for a given location, you can then quantify which areas are really having 6 feet of water, which areas are having 3 feet of water. So how can we really, you know, excavate or, you know, discharge water from those places to outside? Drainage, you know, designs that you want to design based on that. So bathymetry is also needed for our case. You saw that from our field trip, and you had somebody also, Hema I think, was showing how important understanding the bathymetry for looking at floods. So that's very important part. But catchment scale water availability, soil moisture, ET, both for natural and managed system. I will break it down. What is natural system? Can somebody tell me? Without much modification to the landscape, right? As we saw 50 years ago, maybe 75 years ago, how the landscape looked like. If they look exactly like that now, you are saying that it's less disturbed or natural system compared to managed systems, where we remove the trees, we cultivate crops, we build houses by removing trees, we kind of occupy you know, areas that were not occupied before. In those kinds of settings, distinctly, you know, differentiating between how managed system versus how natural system behave under drought conditions, you know, that is very important. That can actually tell you how to distribute water resources under both normal and drought conditions. So catchment scale analysis, which you are doing already with all your hydrology models, you are not doing something totally different. But all I am saying is to separate the signals between managed versus natural systems, how water availability changes under extreme conditions is the one that I am talking. How water availability changes on normal conditions, you know, but under extreme conditions how they are changing is the one that I am asking. That is a question that is not answered yet. Precipitation is a big factor, right? As we all know, they are the important inputs for hydrology models. But how do you validate precipitation? You need multi-source precipitation data, whether it is satellite derived, even within satellites you have so many different model outputs available, resolutions available, accuracies are different, and then model derived reanalysis products are also there on top of fields based or in situ based observation measurements that are gridded by IMD or other sources. So multi-source precipitation analysis is very, very important to understand how they will impact rain-fed agriculture particularly. It does not matter for irrigated agriculture. Why? Why it does not? Why this analysis does not matter for irrigated agriculture? At least on the research level. It is important to quantify them for that also, but why am I saying that this is more important for rain-fed agriculture than irrigated agriculture? Yeah, that is, this is directly dependent on the rain, but why irrigated agriculture? They are also needing water, right, from irrigation, I mean precipitation. Correct. So we have reservoirs, it stores water, they are shock absorbers and then they can deliver water when they need it. So rain-fed agricultural systems are more vulnerable to drought than irrigated agriculture, right. In India, for example, there are several places like this, interior parts or the mountain shadow regions, all of those places that are rain-fed agriculture where this precipitation analysis is very, very important. You cannot rely on one station precipitation approximate for the whole area. You need high resolution precipitation. Assessment of inflow, outflow and diversions for multiple anecuts or barrages or diversion structures that I am talking about here, and develop new rule curves. That is a new topic, hot topic actually speaking. How do you develop rule curve? What is a rule curve, by the way? Anybody knows? I just want to ask some volunteers here except you. Anybody else? What is a rule curve? You have all heard of rule curve, right? Have you heard of rule curve? Raise your hands if you have heard of it. Nobody? Oh, one or two only. Okay, two. That too half raising only, not right full raising. That's okay. So not too many of you have heard of it. What is a rule curve? Rule curve is nothing but they develop what is the supply, what is the demand for given month, and based on that they are going to come up with this much of water that they should release for Jan, Feb, March, April, May. So based on long term calculations of what is the inflow, what is the outflow, what is the required supply that we need for meeting the demand, that is drawn based on the observations. That is changing over time because of the supply is changing, the demand is changing. So the rule curve has to change, but we haven't changed that in many places because of lack of data. If you have high resolution data, you can develop new rule curves. That is very, very, very important. And in India, for example, I would say under flood conditions, people still use the old rule curves, thinking that they can just release the amount of water under flood conditions based on the inflow. But the inflows are really changing now with all these extreme events, huge quantity of rainfall that we are getting. How is it really impacting the release of how much? The person who is operating the gates, they are going to refer to that graph and say, oh, 8,000 CMS that I need to release for January, which was developed 50 years ago, that rule curve, right. So he is going to release the gate, 8,000 cusecs or cubic meters per second will be allowed to go. But is that happening today? Probably 80,000 CFS is coming or CMS is coming upstream, but he cannot violate there are legal complications to that. I mean, it's not just based on observations and he can go and change on his own. It's all liability issues in many places. If they violate how much they open the gate, it can be questionable, right? So they don't want to violate. They don't want to revise the rule curve because of legal complications associated with that. So you have to remember that bringing new ideas into developing rule curves is a significant part of how we maintain all these water bodies in the country. Investigations on decreasing stream flow due to land and water resource development, check dams, farm bunds, laser leveling, surface water storage structures. So there is of course significant variations in stream flow we saw from Ankushapur. CWC can give you that information on how many streams in the country or gauging stations in the country are showing a declining stream flow trends, right, and how are they impacting both land and water resources development projects. There are already check dams, there are already farm bunds and water storage structures in all those places. Because of decreasing stream flow, they are changing. In the US, what happened was, in one place they had hydropower projects, turbines were installed in the outflow of the reservoir. Using the head generated by the falling water, the turbines rotate to generate electricity, right. They are converting potential into energy, electrical energy or kinetic energy, right. So that is actually dead when there is no water coming in the river. They had to shut down all these thermo or hydropower projects. The reason was not enough water. So what happens to these operators? These are contractors that operate these hydropower projects. They are obligated to generate certain watts of power and give it to millions of watts of power to give it to the clients of, let's say, a city like Hyderabad, a hydropower project installed in Nagarjuna Sagar Dam, let's say. If they don't have enough water, if they don't meet the requirements, contractual obligations by these operators of hydropower projects, if they cannot meet, they are going to be answerable to all these people who are relying on that. So we don't know how this decreasing stream flow will impact those structures. Assessment of decreasing reservoir capacity and silting. Example, I put Nagarjuna Sagar here. It was done before, long back, but that's a problem. These capacities of these reservoirs are decreasing because of siltation. The sediments coming from the upper portions of the catchment are reducing, are piling up over these reservoir sites, and they are decreasing the capacity of these storage structures, and that is a problem. Can we quantify what is the reduction in the size, and why is that aggravating because of climate change or land cover land use change? We don't know. Those are the questions to ask. Land cover land use change for changes in irrigated and rain-fed agriculture related to evapotranspiration runoff assessment should be done. It's one of the basic question that we want to ask. Remote sensing based cropping pattern, evapotranspiration, reservoir storage. This was basically my research goal, my own personal research goal, established a few years ago, and it is going to be answered with what? Can you tell me? Relate to an incident that happened recently. What is that? Nicer. Exactly. We can answer that question through that product. This particular question is very important. Human impacted water cycle and carbon cycle over regional and continental scale. I think you have been seeing this for many times. When I call human impacted means how much of a disturbance that we are creating, right? It's done at the local scale maybe, or it should be done better, but then how are we actually looking at it on a regional or continental scales? Regional in the sense, I would say big river basins in South India, big river basins in central or north, like that combined, and see what kind of water cycle and carbon cycle that we are impacting. Socio-hydrology with explicit water human feedbacks. It's a big open field. I think some of you are touching that topic in this crowd, I can say that. Socio-hydrology, like humans are really modifying the hydrology, and then how is it affecting the feedbacks. So that's again, it's a broader part, but each of these bullets can have 3 or 4 questions. That's the job of a researcher, to ask how can I answer this particular statement with these questions 1, 2, 3, 4, and then refine your questions basically couple of times based on what's available, what tool you can use, how can you get the output, what do you process. So those are the common things. I think with that I will stop here. I think I am giving it to Dr. Venkat Reddy, who is here already to start his lecture. So this is what I wanted to cover in terms of both mitigation, adaptation, how can you build resilience, to how can you ask questions that are pertinent to your research. Okay, I'll continue tomorrow with a couple more slides on one is about how to do research. I'm not going to take a specific question from here, but I will generalize. Taking these questions in mind, you have to come back to me tomorrow and sit through that lecture. You will understand what I mean. How do you ask the question? Where do you start? What it takes to really do a particular type of research, and how can you summarize them into your communications as a journal article. So that is the last part of the lecture that I will have tomorrow. With that, we will end this course. But for today, my section is ending now, but we will continue after Dr. Venkat Reddy's lecture. For today afternoon, I think SWOT model exercise that we'll have, right? So we'll stop here. Any questions, general, before the transition happens? Thank you again for sharing that video, Mohan. You want to use this computer?
One, like that. Day one only, like day one only. Yes, very nice. Yeah. So mostly, as said, Siri said, like almost we are coming to the one more day to go. So you are, I think, now onwards, like everything, like a concluding type of things, one by one aspect. And then tomorrow, everything will, all the session will continue here only. So just we have the main important thing, as Sridhar mentioned, like a. So we are all told, we are explaining almost, and we are concluding tomorrow one by one. So you have to come with the, you can say, one is like a feedback, like what exactly the way you want the things, whether they are not. That's one thing. And main like a questions, like a, from whatever you understood, how you plan your research, how you plan your like a projects related to your either your MSc projects, or whether your research work, or in when your organization, how you plan your works. All things we can come there, we are there. See, there is a exclusively keeping some time for to get all the things, and we will take some questions like how really you can take further your research work. That's what is our main intention, that whatever you learned here, that has to be useful for you once you go back to your place. So with that, just before going to the today's class, like it is all like some of the things like instrumentation. So as we are discussing the other aspects, right? Today everything like a modeling and then simulations and all the things, right? What is the basic ingredient for all those things? Data. So for data, so what is the main source? So instrumentation. So unless there is no, you can say the, you see other day you saw like how much you can say the things are going when you see the instrumentation in the water, or you can say basins, or you can say watersheds, you can say. So here today we will see like a what is the like a, as you already some of those things already you come across in the lab, like you are already saw in the field, and some yesterday I think Sridhar is already gave a brief like connected whatever that saw you in the field, and then how those things will be connected as a data sets you saw already. So I will little back like instrument side only, just we see some instruments what are there and what are the changes are occurring, and one new concept that like there is something called open hardware actually. So like nowadays like open software is there, right? Like that open hardware is there. So that really how that really make a sense in this I can say the simulating or understanding sensing some hydrological process. So those things just I will introduce, and with that I will stop. So here this all comes under the one main important concept like a right now all this instrumentation and related works, this comes under the field hydrology. Okay, now you most of the things like hydrology, all things you study, right? This is like a one specific, we can say the one sub domain type of thing called field hydrology, where all these issues like what type of instrument has to be used for what measurements, how they have to be maintained, what are their specifications, how their calibration. So all things comes into this one, and of course general techniques, and then of course this is what I am saying. So you will see one by one quickly. So this is the like a main thing here, like we are using the, you can say, field based observations, so understanding the hydrological process. Okay, this is the initial like a one stage, this is the one of the main thing. So all the process they are observing the in the field and then studying the hydrological process. Later they are evaluating data sets, later we develop models, and then later we shift it to the all modeling type of things. So but this is the main core thing actually. So it is like only measuring, and of course involve all the things. Okay, so now the you can say things like a whatever the you can say point observation, now the shift is from point observation to the spatial like aerial observations, like what the NISAR mission or otherwise previous like a microwave or soil moisture. Now field point to aerial thing. Only thing is of course we need to have proper calibration things. So this will all provide a lot of, we can say the things it is useful for spatio-temporal quantification, it is useful those things. Okay, this all like a lot of, we can say, things. So the main thing like all of you last 3-4 days we are discussing about, all these things are connected to this thing. So their effort like other day like mentioning, right, whatever they do like what some graph or some data and making in the notebook, those things finally they will help you to do a very good calibration validation, that we will rely on our results. Okay, so it is like a, I said like a forecasting, this instrumentation is will make a one of the important things. So otherwise you can't verify, right, how much is with the forecast correct or not. Okay, so this will the, I can say the whatever the advance now with this thing, right, a lot of things we can do with the current like a, we are yesterday we were discussing about some machine learning, those things, right. We have some field data is there, with that we can take as input and we can do lot things. That's why things we are working. So that also I will just tell you briefly. So here it is also very much important in the integrated water resource management. That's what I think Siddhar also explaining some like AWRM, integrated water resource management. So a lot of instrument is there that you will get each and every parameter, accordingly you plan your water resource available water resource and then you can work. Okay, so it is all like a lot of, we can say, the connected things. Once we have the one data set means it will create so many quantitative, so many things we can do. So it is like a type of, we can say, things like a from starting any simulation to decision making to conflict resolution. Like a, for example, two interstate problems are coming, where they will check how much data really available water. So they say some many TMC, they say some state so much TMC. How we can that resolve actually? So once again they are saying with this field means like a measurements only. They call telemetry. They will go and measure the for the years. Accordingly they will decide how much water each has to be shared. So these are all the things actually. But now like everybody like making lot of things related to the model, like say modeling thing actually. But not things can be done at the data collection also. Lot of, we can say, developing a new sensing techniques, developing new field observations, data, you can say spatial temporal observations. That is one of the area actually. Lot of things can be done in that particular thing. So here, so all the instrumentation if you keep, so what is the fundamental basis actually? That is watershed. So you remember other day is showing that he put instrument, somebody asking like why it is there only, and how that has to be kept and how it will be decided where to keep the instrument. So like other thing like a other type of, we can say like a roads, other thing, that is a different way of sensing, right? For us is like anything we want to sense means, especially we want to measure something, you need to find some correct location. So or like whatever you measure, like how that we can say the quantification, those things will be connected is as a, the fundamental unit for us is a watershed. So you keep a rain gauge station, you keep a, well, like whatever the, you can see the water level recorder. So they are like you have to see where the, what is the outlet, how much catchment area it is serving. So those are things you need to know those things. Or you need to plan instrumentation watershed like that. So that's a thing, since that is like a scientific unit to do all the later simulations, all things, that's why we need to give the instrument also like that. So it is like a, you can do the something like a basin level, right? So many instruments we are seeing, right? So some people like asking like a basin is there, like I am working in some other place in where the data is not there, then how we can work there, or you want to make a say different type of experiment you want to carry out. So for that normally the people can do this, this is called actually the experimental watersheds. So many places like some universities, so they will run this one. So experimental watershed, even the National Institute of Hydrology, so even the like we have some of things organization I will show you, they will have the separate thing, they will do entire instrumentation, they will keep there, that has a model basin. So for all checking your models, for example HHMS, across or something other models you are developing, right, you can check there with all those models. Okay, they are called as experimental basins. So now all those things are like maintained by, now for our Indian case means we have the CWC, they are doing all things, or any cases some of the institutes, so they will keep the experimental basin to keep all things, every instrumentation they can we can see in that particular experimental watersheds. Okay, so normally each river basin they will have some at least 1 or 2 experimental basins to have all the data sets. Okay, so they will act as a like representative things to keep all those data sets. That's like we can easily the surrogate basin, like we can test there and we can transfer data. Other day some people asking like how we can data transfer to from one small basin to a big basin. So once you can able to set model means similar physiographic parameters are there, right? Same you can say the geological test is there and topographical thing is there, we can easily change the parameters. Okay, so these are the you can say all the instruments already just like you are seeing. So if I say in the basin, you tell me the what type of you can say the process will be there and the instruments will be there. These are all things same thing like a 5, 6 I kept here. So you can just quickly you can tell most of you know at least one way or other like what type of instruments you are going to use. So rainfall means rain gauge, we have the latest thing is the automatic rain gauge stations, automatic weather station they call. You can get rain along with so many 5, 6 parameters you will get. Then go for the stream flow. So already you saw thing, but there you don't have the only the physical measurement they are doing, but more accurate measurements means they are using current meter you are seeing, right? Those things already you are seeing, right? These are all already there, yesterday you saw that one. So next level means advancement to this one is so ADCP, so acoustic Doppler current you can say profiler. So that will give the exact like a depth, especially big basins, right? So there you can't work with these things, current meter you can't keep and then you can't try, right? So there the ADCP will work. Okay, so that is the you can say the instrument. So then you tell me about evapotranspiration. So nowadays like a flux towers we are one of the things, and eddy you can say eddy current meters will be there, especially the eddy towers, that is different actually. So those things, and then we will have the so flux tower, that is the latest one. Otherwise we have the old our standard Indian this thing means yeah sorry. So that is so these are some of the things are available. You can this is like a traditional you can say the class A pan this thing. So any you can say the basin you see that will be there, that is a standard one. But now lot of we can shift it there. Now actually satellite, that's where we can get the data set. Okay, so evapotranspiration estimation by satellite data set, that is will be the one research area. So where you can say lot of you can say data sets. Other day I am showing about that MODIS data sets. So there you can get the data, and then from there you do some equations, you can get into the evapotranspiration. So that is the that will have a lot of you can say thing, but all the of course field checking all things you can do with the things. So of course groundwater. So the mainly groundwater means the two things only there. One is related to depth and other one is what? So we are worried about two things related to groundwater. One is depth, other one quality. Like so many parameters, like what are the cations, what are the anions, what are the different you can say the parameters, almost like a big list will be there. Normally anybody make the groundwater. So like all those parameters 10, 11. So normally it is a sampling technique. You do the sampling and then you will measure. That's the groundwater things. So they all combinedly you are providing your own basin. That is we can call as an experimental basin. Means everything is there. So all these things you can able to understand different process. Okay. So the other things only here what I am showing. So some of these things are all also important, like a sediment. So it is like a automatic. This is like a simple groundwater automatic manual. Means like if you are this is like a bore well or is a observation well. So they will just like a dump this one, like wherever the you can say the fluctuations in the water levels that will be recorded. Okay, so they only automatic you can say every day piezometer type of thing actually, the pressure those things you can get. So their quality means the sampling, that is we can't, but here we can get a piezometric, you can say the pressure. So those things we can get. So here of course sediment is one of the things. Yesterday you are seeing, right, they are not only measuring that in the river basin level, right, there will take some, actually the sample bottles will be there, samplers. So they will collect the even sediments that to sample water, so they will analyze for sediments, how much sediments are there. Okay, so they will frequently miss for that gauge station whatever visited, that is not there, but other places we will have that sediment sampler. So that they will go on select collect, and then they will do lab test, and they will find out what are the different like suspended solids, all things they will find out. That's also very important for so many studies. Of course soil moisture nowadays, lysimeter, those things, these are all like a very important field measurement instruments. So you can give from plot level, plot means only one agricultural field, to the, you can say the basin, that way the all the instrumentation can be planned. Okay, so this is of course water quality I mentioned. So this all things whatever I explained, let they will come under the two broad categories. So it's like a, whether you are doing a continuous measurement or it is like a intermittent measurement. Okay, so continuous measurement means what, actually the here other day they are showing, right, whether it is a continuous or intermittent. So the continuously they will do, but it's like a time by time, actually intermittent, actually they are doing the, you can say only daily twice like that they are doing, but they are continuously doing a thing, but not a continuous time scale, like a rain gauge is there, you can't see the complete hydrograph, right, what type of things may not be there, like whatever they are doing. For example, automatic weather station, those things are there, we will get a continuous data set. So only thing is for the time we are dividing into different time levels, but we will get a continuous measurement. So now that are the two things. So depending upon the different type of problems, this type of, whether you are going for a continuous or intermittent, comes into picture. So this is like a in situ continuous measurement, these are all the, most of the times weather stations, all the things. So here intermittent means like a only velocity, hydraulic conductivity, those things will come. So intermittent means like hydraulic conductivity in this thing, only few times you will collect actually. So most of other classes either a point or aerial. Most of the instruments go for a field, means a point you will get. Few only we will go for a aerial, especially the this type of, you can say drones, these things comes means they will come under the aerial platforms, aerial measurement will get. Okay, now slowly shift is toward this aerial measurements. Only thing is some checks we can do with the field instruments. Okay, so now what is the current you can say thing. So current all the, you see, I think most of your systems you are seeing, right. So sensor based systems, automatic weather station, they are all like a sensors will be there, you can work with those things, and it is like a, for every sensor, like a, for example temperature, the one sensors will be there, temperature sensor, pressure sensor, like that. So every type of thing, so we can go for a one type of sensor type of equipment. Satellite based techniques, so even precipitation also we can get by the, you can say satellite systems, right. TRMM, so many missions are there right now to find out the rainfall will be based on the cloud, otherwise whether the rainfall is occurring, what is the amount of rainfall, the aerial based, you can get through the satellite techniques. Okay, it is one of the important things happening in these measurements. So here now this concept, like a interesting thing, this is like a open hardware. So what is this open hardware? This is one of the development in this sensing techniques, especially field based instrumentation. So what is this one, open hardware? So anyone we previously heard about this open hardware, like a open source software. So open source software, you know, right. So everything like a equivalent, like a, we have Word document is there, for example Microsoft, equivalent we have the other things will be there, right. Unix, Linux, one the system will be there, Unix system. Linux is like a open source, right, like a, that type of things are there, right. Same thing like a, so many softwares are there. So everything like a proprietary will be there, like only proprietary they are maintaining, licensing will be there. There is equivalent to lot of open source are available nowadays. Okay, so like a same thing like a concept for software, why can't be for hardware? That is the starting. So now like you see like a weather station, I say normally somebody will come, proprietary person will come, right, they will install the instrument. So we want the rainfall in one way, like a, for example every 5 minutes we want, every 10 minutes we want, so like that. But they have their own like a thing, and we want to see what is happening in the directly in the instrument and what is happening, and we want to see with us. But normally they have all instruments, right, they have their own software system will be there, that will go first there, then they will send us, only we are seeing in their domain actually. Okay, and means a lot of times we don't have a what is happening in the system, whether really serving our some example, some specific research you are doing. So whatever the way they are, some commercial instrument is doing, that is not okay for you, you want to do separately, that we can't do with the proprietary hardware instruments. Okay, to solve all things now, it is like a same thing how we can apply for the this software, open software, that open hardware came into existence. Okay, so it is something like this actually. So it is like a, for example, drone, you know, right, drones. So drones normally what they will do, they will like some commercial item they are building, but now it's not required, right, you know, like all the components, if you can order like what are the things, price will be there, so you can take that one and you have your own thing and you can assemble and you can do that one. For that, no, you can say so much, you can say the what technology, whatever, you need to have lot of things you need to know. So minimum things they will make according to the component and you can build. That's what I think. Same thing which is available in a other systems like a like ECE and other domains. It is taken to the is water resource thing also. That's what I want to tell you. Field hydrology thing. That's what I want to explain here. So this is all what I told right now. It is available. Open hardware means it's not nobody's proprietary. You can't say that some trademark like a source of company manufacture like that. Component wise you can take and you can build, you can assemble and you can use. Huh? LiDARs means that is like a, you can see like a, that much like a, like it is all like a depending upon the type of, we can say the technology there. So much you can think means it's very difficult. Few things we can easily go for open hardware. Okay. So that all like a, how the, I can say all the source code has to be available and the technology, the drawings, those things, sensors has to be there. So like so many other connected things have be there, then we can go for the, do that open hardware type of things. Okay. So here, the open hardware anybody say means that is like everything has to be available to anybody, they can work, and this all source file, especially code, anything like all the things has to be available to all the people. Okay. So it is like a, anything like a, it is not only somebody will do as per their requirement, right? If you know the other insights, anybody can do the anything like a development. That's what is the main thing. No, nothing but like a, somebody as a proprietor. Okay. So it's like a, this is what is the thing. It is like coming with a new way of developing the instrument, required instruments. Okay. So why that you can say we are so much interested in this open hardware? That's what I am saying here. Okay. So you can make tailor end, like what is the way you require the measurement, that way your instrument you develop. Like previously is like a, whatever they are giving we have to use, right? We can change whatever the way you want, you can about accordingly you model, bring the instrument and then you can make. Okay. So it is like a, so you can make the software, everything is accessible to you right now. You can write your own code, see that directly it will come to model, especially forecasting type things. Instrument, everything is in your control means you can easily model, right? You can easily do that one. That's what is the thing. So especially the cost actually, the you can say for example conventional rain gauge station, it is costing around near to 1 lakh automatic weather station. So if you are really able to survey, do market survey and then all things, if you able to bring sensors, everything, we can do within the half of the amount. That is possible. That things are possible. Okay, but of course you have to do lot of work you have to do and then you have to build that one. Yes, that all things once you are building means the first job is that only calibration and then checking the accuracy of the things. So that's where other day we are visited right site. We also brought some instrument, you remember. So we want to check the, you can say that thing. Why only we are checking there only? Since already CWC is doing right already some instrumentation, their data is there. Later we can calibrate. Otherwise, how we can calibrate our data set? Rain gauge you are being rain gauge, for example, you are building. You have to have some already existing rain gauge. You have to compare, calibrate, check. Then we can use. Okay. Otherwise, you need to do some lab scale things. Study first you do, check, verify, then go for the field scale. Okay. So here, so many you can say the things are there, like especially the who are doing, like you can ask like where I can get all these components. It's all like a very, I think if you are click this something, you can get lot of, we can say the things like even now 3D printing they are saying, right? You want like something like you send something like I want this type of board, like where this circuit board you want, if you say means they will make for you as per your requirement and they will give by this 3D printing technique. So this is like I think most of you at least heard sometimes this Arduino. It's like now that that is the main thing in the open source hardware component. So you can get to this one and then whatever the this is like all microcontrollers. Whatever the way you want, you can collect and then you can use for your system. It's like a generic thing. So somebody want temperature sensor, so you can use this one Arduino. Somebody want rain gauge, somebody water level recording, somebody like only acoustic waves. Anything we can use a common Arduinos will be there, we can use. Of course, this is like one more place where you can get these type of things. Okay, you can check and then sometimes you can really interest, like at least suppose some of you are the faculty are there, like you can give to students, like they can easily BTech students, right? They will feel nice to do this type of things. And a conventional modeling sometimes they may get very difficult things. Oh, okay. Oh, that's the thing. Okay, very good. So yeah, once means you can take from the open hardware, but for example you do right, you are way your own building, right, your own concept you are preparing means later you can take patent also. But if you do patent for your means that cannot be other people may not use, that thing will be there, that depending upon things. But whatever the already you are taken from open source, still that will be the open thing, like people can make use. So here some of the thing, like actually the any especially for our field hydrology, anything will we are developing, the three components will be there main. One is sensor, second one is microcontroller. So sensor data has to be connected to microcontroller, right? So from microcontroller to software. So field to system, right? That's the where the how the instrument has to be there. So these are the three important components. So there is the one group of we can say the things, instruments, second group thing. So whenever you are developing thing means you have to look for these three setups. So you have to bring some hardware sensors. For temperature means temperature sensor you have to purchase. So control means like Arduino the type controller. Open source software means like you can see like there is a software with a micro Python like that. Some tools are there, programming tools, tool box or tool setup that you have to use. Okay, some cloud you can say the open source visualization you can use. So with all things you can build complete your setup. Okay, so this hardware sensors they will be like normally the things which are collecting this environmental data set. So they are the main important things which will translate the data into the you can say the from electrical signal to the digital data, and then that they are sending. So this is like a sensor will take and sending to the instrument. So here so they will the I can say main thing like they will work with like a lot of times like a power system you have to be provide some electric energy you have to provide to collect data. So that will collect that whatever data it is collecting, it will generate some signal that will be counted into some analog maybe number that will send to the microcontroller. Okay, so it's like a example is like these are all things like for example wind, this even rain gauge tipping bucket rain gauge like for example is there. We have in the market like for example anybody want like sensors for this one we will get it. So like a similar like a wind this thing, and you are saying like air quality, turbidity, so many are there available like that sensors. Okay, this is like a one tipping bucket rain gauge sensor, that thing that whatever I am showing there. So that is like a some typical examples. Okay, they are all like a sensors. Okay, so you can just like ask this like a sensors, you first of all identify for the parameter you want to measure, see the sensors and then accordingly you purchase. Then microcontroller, so it is like a circuit actually, the data electric signal, right, it has to collect and then make into the digital value. This is the duty of this one actually. This is the exactly the act like the brain actually for the whole thing actually. So it is like all the things how much you can see you want to make it into the, these are all things Arduino, these are all the things available. So people nowadays like you see lot of things you will see when you are checking, these are all comes under that thing. It's one component. First connect data comes to this one. So this will go to, from this data will go to software. That's the thing. The third you see the component, these are all the different type of circuit boards or controllers. So they will act like a mini computer. That is you remember like that. So like they will do whatever you are doing in computer, right? So many things we connect to this thing, right? We will see all the things, how signal is coming, signal is changing, storing, everything we can see when you collect with the system. So here from the I can say we need to the I can say this is all like a transfer protocols actually. So sensor you are getting previous one, right? Previous one what you will get only in the control it will come, right? From there you need to go to the like the field, there only you are collecting or you are sending to some place, other place. Then accordingly all your instrumentation will come. Wired, wireless. For example, the system you want to see here, but you are doing somewhere in the field. From here to here you have either wireless or wired. So for example, telemetry is there means from that previous instrument is there, right? For example here. So this instrument we need to collect with the one more thing actually. So that is like a either SIM or the you can say other things. So that for that we need to have one more circuit board, small circuit board, which can convert the data which is available in a this to we can say packets, then only we can send to the SIM, right? That thing we need to have one more circuit, like it's like that. So you can see these things. There are like a different protocols for this one. So most times you don't need to much worry, means there is nothing is like electrical, you think that easy like that, right? We have to know something is required, then accordingly you can try, or you can ask some of your this thing where the people are there, they take selection, accordingly you can use. Or nowadays lot of in everything they are providing data set, like how you really can use. Okay, these are some of the things actually. So this is like a thing. So previous one is right, you need to have the additional connection of this one. So you see some place where we can keep the chip will be there. Sometimes Wi-Fi means no problem, otherwise we have the chip to data to get to SIM actually. So that is like you see there is a location for the your you can say mobile this SIM card. Okay. So then last one is the software. So this is like a platform will be there, like Arduino means Arduino platform will be there, like other things are there. The data, like I said, like it is a computer, right? We need to visualize, right, what is happening in that particular data sets. But all things we can do here actually. So some C++ programming, Python, whatever the things, right? Lot of things we can make. So whatever conventional programming you are doing, same thing we can work here also. Okay. So we can do a lot of, we can say libraries are available and we can try. The duty is you have to see that from the sensor it is coming to the controller to the whatever the things finally to the system. That's what it will do exactly the things. Okay. So it is like a lot of things, like one is like a commands, means you want to do something, error is there, you want to send a command from system to sensor, that all things we can send. We can any storing we want we can make model. So like a time step you have to define, right, like a rainfall every 5 minutes. You can do that programming here only. So every 5 minutes that packet whatever is coming you send to the sensor, that we can tell. Okay. So it's all like a getting the data set. So here I said like we are also like working some of the I can say aspects, like we can say the open hardware you can say components. So we are tried like with the rain gauge station. So then we are also like this is the one you can say the automatic weather station with some of these things. And this thing is like actually like we said like Sridhar and we are working with one Spark project which is related to the modeling. But the same Spark project, the main goal is to develop this one only. So the low cost open hardware watershed monitoring system that we are working. Like other day Hema one scholar she showing to you like all the one instrument we are trying to checking in the river. That's the thing only. Like we want to see the bathymetry, how we can do that one. Okay, this is all like a funding. Right now it is working with like right now how we work previously. The same we are working with one more. There is a Tennessee University. We are trying that particular work. It is on-way. It is ongoing work actually. It's a complete team actually who are working on that project. So it is like I said like previously also but this is all like a proprietary things like but same thing we are using for the how we do for our normal right now the instruments we are doing. Okay. So like right now hundreds and thousands of instruments are there, but who will do work make the database of all these things. Okay. And lot of anybody want to do the you can say this one like a storage, and then so all things are coming, right, they have to come into one particular place and we have to visualize, right. So for that India we have this one National Hydrology Project. CWC duty is to collect, but to make a base or like how many gauge stations to increase, how many rain gauge stations you to keep. So everything they will monitor actually. This is like a now current actually. It is implementing in different phases. So now it is the second phase is going to start. First phase is already completed. That's why in the India right now we have a lot of measurement systems. Other day you are seeing right one software. First day India varies. One of the project that developed under this India this National Hydrology Project only. So this main goal is. Second phase already started actually. The already it is commission means like a one. So they like all NRS they are all involved actually. I think even irrigation department is one of the what we call stakeholders in that whole things. State irrigation department, central, so all the things actually. So this is like it is all like to collect coming from different sources to maintain the data set. So this is like a World Bank is supporting this one entire thing. This is what I am saying like a second phase right now. Our first phase is all over. So it's all like a making every network modernize. Like other day you are seeing like a lot of instrumentation they are developing and they are going with the new concepts. These are all possible through this one only. So making more number of stations. So you have the more number of stations means more data you will get. More data means your simulation will be more correct. So more reliable. That way it will be useful for the forecasting and other things. Decision making is more easy. Okay. So it is like This is like a 3 important organizations in India. I think this you have to know who are people who are really want to work. So things like one is Central Water Commission. This is already you saw the other day lot of things they are doing. Second one is IMD. This is all first day itself you tried and then we are seeing some of the things actually. So other one is more like a research. So some of you are there from the NIH, right? Who is there from NIH? Institute of Hydrology, you can say doing your project. I think that's yes. Internship, you are gone to the Institute of Hydrology. I think some other also we are some people who are already connected with NIH. Yeah, presentation of the NIH. So they like a field scale you are saying, right? Lot of small experimental weather station they are maintaining, and all the testing, for example, any model, whatever you model you say, they will have a lot of places for to testing, and they will say that okay, this is the reliable, these are the parameters. So many parameters list we will make, right? They will make for the Indian basins. So here this is the NIH. This is basically the research. It is a collection, and it is like IMD is related to mainly related to the climate parameters. They are related to the hydrologic parameters like what is the water levels, all the things. Okay. So the finally the summary is this like I said like, so it is very important, like we will only bother about data, but always you have to see background how the where the data is originating and what happens. That's why we put intentionally that particular you can say the part in the our program, so that you have to feel that how things really happening in the ground level data collection. So that's like it will make us like a better understanding all our hydrologic process. So like they will make our more like a field hydrology or lot of you can say the you are getting. So it will take our hydrology like a further better, like we will come to know more intricate things which are there in the field scale. Then we can easily implement them in the models actually. So main thing is like maintaining those instruments itself is a very big challenge actually. So they say National Hydrology Project like I am saying, right. So they will make up to the budget available, they will very high end instrument they will purchase. Then later maintaining is very difficult. Same thing happened for us also, like I told, right, we are installed some instrument in a nearby station, but where we can miss, like it is always like some 50 kilometers away. So we put the weather station, rain gauge station, and then all things. So like sometime we told farmers to maintain, but later it got very difficult. And for example, that solar panel, people will took away that one actually. Solar panel means we can't get the remaining things. So flood come means that it will wash away that all things, nobody will bother. That's where like a lot of maintenance is the main thing. It's initially will start, but especially this thing, somebody could able to maintain any like experimental weather station for so much time, experimental watershed. That itself is a great thing. So somebody like really any institute or those things, it is a very good thing actually. So that people later do lot of work with the data set. So of course like a lot of we can say the concept now. We will see data, but you see like the especially what unit that is giving. Sometimes like the other day you are seeing, right. So QMX and QSEX. So like that lot of difference will be there when you are input in the SWAT model, other models actually. And what is the measurement they are using? Like what is the benchmark means what benchmark they are using. It is always important to understand those things also than only just looking at data and then go on working. Okay. Of course, like a lot of we can say thing like we can use the lot of we can say research with the repositories, but only thing is you see with something like some field observation also you include. Whatever you do research, do something field observation concept also is there. That is like make you more understanding the concept. Other only we do SWAT model and we doing this thing that may not make. So at least visit watershed means that watershed you have to visit. So you are doing some simulation of the watersheds. You have to visit the watershed at least few times. So that is the means whatever I am planning. So let's open for discussion. Any questions? Yeah, that type of things are there actually. I said like IIT Roorkee and especially the IIT Roorkee they are having other things. NIH. So there are like experimental plots, you can say plot scale to small you can say basins. It's very small like 1 square kilometer, even half square kilometer, that type of things are there. Then only you can do like especially small things you want to construct in the basin and you can try those things. Even the Manning reference coefficient for example, you can't try on this thing, like you can try on the small things, how that really influence the flow. The things are possible. That's why you less than half square kilometer you can have the field scale. Field itself is a one basin, like for example this room is there, water everything will go to one place, means that is itself is a watershed. We can have lot of instrumentation there itself. Number of watersheds, small things. Yes. Any other questions? So for questions for you now. So why field instrumentation is important? Extreme events. So you need to like a lot of, you can say design curves you have to prepare, right, like a 50-year flood, 100 years flood. So thing means all those things how they will do with the field instrumentation only, they will all have a lot of things and then connected things. Now this you have to tell. So what are the event based model, if I say what is the important, very important things, parameters. Event based model, for example rain, like a flood event. Normally what is the field level, what you have to measure? Discharge levels, rainfall, and one more important thing especially for event based model, temporal only, temporal like every minute 10 minutes like that will get, but more important soil moisture, you know, initial soil moisture, that is very important, otherwise you can't get the flash flood is coming. So that depend upon the how much soil moisture already there in the basin. So many times we will miss that one, so that we can't really simulate that peak, we can say the flood or when the peak will come. That's very important actually. So virtual basis can we measure the, you can say the stream flow. Stream flow without instrumentation also I will, from here itself I can see that how much water level is there. No instrumentation, is possible. It's possible now. The satellites we have a separate, you can say satellite systems. First day I mentioned actually. So there is separate group of satellites are there. We have the even our ISRO is maintaining that one actually. So the day one I showed you that one, the one thing actually we have the virtual, you can say gauge they are called actually. Every time the satellite will come there, that will give the, you can say the depth measurements. It is a data you can get in the open source. Okay. It's reliable means like they will number of times they will get right. They will calibrate same with the gauge points and they will get actually. Yeah, it is there available that this one actually. Not reanalysis, it is observed. You can get, for example, you are getting the water level. Other day they are giving what finally, what is the finally you are getting level, right? This also will get the levels. Okay, that is like a from the, you can say the satellite measurements you can get the levels. Like a sea level like that you will get, right? Same thing like a, we will get the water level, water bodies level you will get, reservoir levels you will get, all things. In the Bunidi and we have the separate you can see satellite systems which are only for doing for this first, only the depth of water bodies measurements. Okay, that type of satellite systems are there. Exactly the satellite system exactly I could not recall now immediately. SWOT, SWOT, that type of things are Indian. We have the one that satellite series is there. Only they will do that one. So not GRACE, that exact satellite. First day it is there in slide. It is there. One slide also I gave for the how the virtually we can measure those things. So of course, what is the open hardware concept by this time understood? Means no proprietor. There nobody say that this is my instrument and I am the person actually. And how it is useful for our basins actually? Means we can make our own way, our simulation, our research work. Nobody is like as per data you are doing right now. The data everything you can plan accordingly what the way you require in your model. For example, you want a high each 5 minutes only want you can train like that. 1 minute you want means you can plan like that also. That way you can do. Okay. So yeah, so this is the thing. So I will stop at this point, and yeah, that's all. I think a lot of references we are like what are the things I provided to you. They're all from most of the sources. Lot of web sources about this open. Anybody real interest means it's a very interesting thing. You can see this one. You will get lot of information from these sources. So that's all from my side. So stop here. So we'll. So by 2:15. Once again we will go back to the, I can see our lab at TLC, and then today is the basically we will see for a complete SWAT. That's what is the plan. So like as like most of the people it is useful. That's what we understood. So we will go that one. Okay. Yeah. We want to announce.
అంతే లైటింగ్ ఏమైనా తగ్గించాను ఎక్కడ నేను ఇక్కడ ఇది తగ్గిస్తే ఈ రెండు ఆపిస్తామా ఈ రెండు ఆపిస్తే కొన్ని లైటింగ్
shall we start? Okay. So, good afternoon. Just listen to you. Listen to you. Actually, we shared some files yesterday, no? We shared some files yesterday, but today morning we gave some pen drives, right? So in that we changed the files. You can see the .NET bootstrap file is there, third one, and then last one QSwag 364. That is plugin file also changed. You might have aware of that thing, or else you install the previous one. First QSwag plugin. Some are installed previous one, right?
Yesterday we have shown some websites, right? In that you have downloaded, right? Okay, that is somewhat version change. You install this one first. QSwag 64 install.
If that is installed, it is okay. Otherwise, you can go for this.
It is the same version. Huh? Okay. After that, install this .NET one. Then go to this swag filter and install them. Okay. Swag cup is as it is. Yesterday, whatever you have downloaded and installed, that is fine. Everybody clear? Huh? Install out, right? Swag is fine. Now first swag. Another swag. .NET, then swag editor. It was from which channel? This one first install it. Then .NET change. .NET change. Will take time. Install. Sir, I downloaded 2 videos. Whatever I went after that, what I did. తర్వాత మీ ఇష్టం లంచ్ చేసి వెళ్ళిపోవచ్చు. అదే బిఫోర్ లంచ్ అని ప్లాన్. అవునా వెళ్ళండి సార్. few chairs open here. Seven laptops చూసాను కొన్ని ల్యాప్టాప్లో ఆ వర్షన్ పనిచేయదు చూసాను అవును ఒకసారి చెక్ చేయండి ప్లగ్ఇన్ చెక్ చేయండి Whatever is preferred, that's why we are doing it. You install it. Still running at 3.64. Reboot అయినా అవ్వడం లేదు సార్ .NET is not Bro, yours is done, na? You're ready with it? You are also ready, yeah? Just still downloading it. It should be here, like you just adjust here. So it will move forward because it will take more time. Okay, that installation will take later.
Sir, just 5 minutes. After 5 minutes.
Now you continue after 5 minutes also. In between we will go so much break. Process it will take time.
Okay, sir. Okay.
Otherwise the target we won't reach. Start. See, if anybody is not done, you just sit with whoever is completed. You start again, otherwise you won't finish the target. Okay? Someone sit here. Just keep like that only. After completion, you should start. But before that, you just sit here. Yeah, start.
So I'll briefly introduce about SWOT model and all for just 2-3 minutes. That's all. Not a boring lecture at all. So please. So what is SWOT? It's commonly a physically based, semi-distributed and continuous model, not like our hectothemas and all. There's an event model, right? So it's a continuous model. So it uses the continuous data series, and it is developed by USDA, US Agriculture Department, and then it simulates the impact of LULC, climate change, and land management on water resources. And it is suitable for large and complex watersheds, or we can say basins. The basins like Krishna and Godavari, which is having 3 lakh square kilometers, also we can simulate using SWOT model. So these are the widespread applications of SWOT model. The surface runoff we can simulate using this SWOT model by SCS curve number technique, and then the stream flow prediction also we can do for water planning management, and the sediment yield also used by USLC equation and the universal soil loss equation, that is. So, and then the nutrient and pesticide transport modeling also can be done by SWOT model, and the land use and climate change impacts on different water resources or else in basins we can analyze using SWOT model, and irrigation and reservoir water management also we can done by using SWOT model, this thing. So what are the inputs for SWOT model? We can see like topography means DEM, we can use DEM, and land use land cover maps, and then the soil maps, and weather data means rainfall and temperature, minimum and maximum temperatures, and humidity, wind speed and all. For management related things, we can use the crop data sets, or what are the crop data sets, what are the tillage data sets, something. So overall, this is the pictorial representation of SWOT model for hydrological analysis. What are the applications, and what are the components, and what are the key inputs. These are some of the references. Our group we did some work related SWOT model. You can check later. So many applications are we did actually. Yesterday you saw the website and all. So you can download first QGIS, and then by using SWOT website, that is swotdemo.edu. First we install the QSWOT plugin, and then we need SWOT editor. For the SWOT editor, we need .NET. If you are using Visual Studio and all, the .NET is also already installed, so not required. If you are not using that Visual Studio or else in anything before in your laptops, you can use the .NET files. And then SWOT cup also. So in the SWOT website, they are providing all global datasets and as well as Indian datasets also. What are the key inputs we discussed now earlier? So like DEM and soil maps, LLC maps, weather data, all they are providing in the website itself. You can check. So we used IMD data for precipitation and temperature datasets preparations, and then for prediction of future stream flows, we used the next GDP CMIPS datasets. The links are provided there. And these are the datasets required. We prepared like DEM, we are taking Cartosat 30-minute resolution DEM, and then for LULC we took from NRSC, that is of resolution of 1:250K, and the soil map we took from ISRIC, that is 1 km resolution, and the gauge, discharge, sediment, water quality data we collected from Central Water Commission. So for all are installed QGIS, right? Our version is 3.16, 64-bit. Yes. So open QGIS first. In the presentation we prepared for Munneru watershed. The PPT will be shared later. All the steps are provided in that PPT. We will share that PPT. Yeah. If you can see in this plugins menu, the first option is manage and install plugins. If you click that, you can search Q SWAT. See the difference? If you check this box, you can see SWAT icon here. If you click the SWAT icon, it will open like this. The pop-up will come as new project, existing project, something it will come. I think everyone has done this actually, right? And then we create our directory file to our SWAT project. First, we'll take new project. Already we have trial 1, so I'll do trial 2.
Are you doing right simultaneously?
Directory you can give any directory on. Please avoid C. You can store it in D or either E. Yeah.
So while giving the project name, don't give any spaces for the project name. The path where you are saving also, it should be short path. Okay, don't create inside. Okay, it will throw error. It should be a short path, and the name there should be any no spaces. Don't save it in C folder. If it is another folder is there, better save it in another folder.
And sir. That is not document. It takes time. Any problem?
So it is difficult to run the SWAT in all the laptops. So one thing we can say, we'll go for one row. If one is available with one row, we can go now.
Already three.
Already it is three actually. I need to demonstrate SWAT and SWAT cup also. So can we go?
Sir, restart now.
Just restart.
Restart now. Okay, start. Next.
So first we need to delineate the watershed. Whatever the watershed you are using, first we need to delineate.
Select your dem here.
Whatever the files we share now, it contains dem. So you need to select dem.tif file. You just select the dem file here. And the dem file is shown in QGIS. And then we need to give threshold value of area. So we can give 500 square kilometer. And then you can click on create streams.
లేదు ఒకసారి చెప్పు చాలా
So first we need to import the dem file from here, and then we need to give threshold value 500 square kilometer, and then create streams. Then the streams will create like this. If anyone not getting this step, we have found one error. So for that error, we need to go C drive, swag, and then swag editor. Towdem 559 bin is there, one folder is there. In that, one file called msmpa.dll. But in your laptop, some of your laptops, it is like msmpa_dll. You need to rename as msmpa.dll. If you change like this, that error won't come. In C drive, swat folder, in swat editor, towdem 539 bin folder is there. In that folder, msmpa_dll will be there in some of our laptops. Then we need to change as msmpa.dll. We need to remove our underscore and then dot. We have to put.
Issue.
Sir, I completed all the so how do I
3.16 grass. Third one. Yes.
If you are getting in Toudem error, I will repeat the step. You can go to C drive and then the folder name SWAT is there, and then SWAT editor will be there. In that Toudem 539 bin folder will be there. In that you can find msmpi.dll file. It will be msmpi_dll. You need to rename as msmpi.dll. Then you can come here. Again you need to import dem file, and then you have to give threshold value as 500 square kilometer and then create strings. This is the shape file of our basin. Netravati basin is this. So the stream network will come like this, the blue color line.
How many times I have to give allowed?
How many times they ask me? They ask 5 to 7 times.
Watershed, green watershed, the while we have to upload.
change the threshold value of this, you can see the observed difference, right? It will create more stream network actually. So, but as of now, we'll go for 500 square kilometers area. Otherwise, the process will be more complicated and it will take more time.
Everyone got streams?
Yes.
Streams? That threshold you understood, like in HMS also we developed, right? Same threshold here. If you increase the threshold, you will get less subbasins. If you decrease the threshold, you will get more subbasins. True.
So then we need to give the outlet file of our study area. In our data sets, input data sets,
First see here, first see here. First see.
in our input data sets, we have Netravati outlet. You just open and the shapefile is there, no outlet at SHP. You need to load to QGIS. Just drag and drop.
All of you add that. Just drag that shapefile into QGIS.
Open our input data sets. You can find the Netravati outlet folder. In that outlet.shp shapefile. You need to import to QGIS. Netravati outlet folder. You have shapefile, outlet.shapefile file is there. You need to import in QGIS.
All of you did this step?
You need to drag transfer to this layers window.
Be sure they are taking from that.
No, not from this. You just take from our folder and then you need to drop here. Layers window is there, no, in QGIS. Layers. But we can observe that point, that is outlet, is not on the stream. This is streamlet, right? The blue colored one. So we need to draw our outlet. Please click on the draw inlet or outlet. Click on it. You can zoom it and you can place here. whatever the outlet is not on the screen. You can observe that. So we need to draw our outlet. Click on draw inlet or outlet. Already the option is outlet here. So you need to click on exactly on the stream. Parallel, yes, parallel to that whatever you imported, no, that one. Hope all of you. Yes. So click on OK on the outlet this thing. So and then we need to select. That is our outlet. So you can click on select inlet or outlet. See, one rectangular pop-up will come. We will just confirm this.
Just select that dot. Yeah.
Select that outlet, that's all. By using rectangular pop-up. Yes. And click on save. And then you can see that one selected here. And then we can click on review snapped. Review snap. You can see one snap. And go for create watershed.
Select the inlet and outlet and option.
Designated, huh? Till this done?
Yes.
How many subdivisions formed? It will show you the number also. 1, 2, 3, 4, 5.
From the left side layers, you can uncheck the hillside and dam. You can clearly see the watershed. The 5 subbasins are created. You can uncheck the dam and hillside in the left side layers. You can see 5 subbasins here.
That is not everything. It will take some time, but it will how to bring something. It is running. You can uncheck unnecessary layers. You can uncheck. It will look like this. Select. Next step.
And then we can click on OK. If you click on OK, the step 2 is highlighted here. That is create HRUs. It was enabled here. You can see step 2 is enabled. That is create HRUs. If you click on create HRUs, the window will be like this.
All of you open this window. Create HRUs.
We need to give another 2 important input files here. One is LULC map and then soil map. And then lookup tables, yes. First we click on select LULC map here. In your input files, LULC folder will be there. And you can select LULC clip.tif. .tif format only. And then you can select land use table as use CSV file. Land use table as use CSV file. First one, select land use map as
Close it and again open. Same process. What are the errors showing? Huh?
After that, you can select the soil map. The same steps here. So in soil folder, we have reclassified India soil map. India soil.tip. You can select there. And then again, soil table as use CSV template. You need to give soil map, you need to give LLC map, and the table says use CSV files. Can I go further?
Yes.
Yeah. So you need to select set bands for slope percentage. Slope here. Set bands for slope in percentage. Set bands for slope. You need to give 2% and insert and 8% and insert. You can say slope bar as 0, 2, 8, 9, 9, 9, 9. And then you can go for read. Read here, right side. Read.
Click on read. After clicking read, it will ask you to choose two files.
Yes, sir. 2 and 8. Separate, separate. 2 insert and then 8 insert. % is different, 8% is different. And then for LULC, we are having Natra LULC.csv file. I think it is there in your input file.
First choose LULC, then choose soil.
Soil. There are two different files. First you can choose LULC file and then soil file.
Don't choose reverse.
And then click on read.
It will take time. Don't click so many times here. It will take time. Don't click. It will take time. Don't click so many times. How many HRVs? 27.
First time I'm working on sweat. I heard about this model, but I have concept.
So you understand what is HRU? What is HRU? So with this step what happened?
LULC and soil maps.
We have given LULC, soil, and what is one more? Slope. So with this, how HRUs will create? So first land use map will be there. After that, our soil map will be there. After that, our slope map will be there. All three raster, it will identify the unique combinations. Combination of these three into how many uniques are there. Okay. One type of land use, one type of soil, one type of slope. These three will be combination of one HRU. So like that, it will identify how many unique combinations are there. So after this, you will get to know how many HRUs are there. I think 127 are there. So in this basin, 127 HRUs are there. So like in the HMS we have seen, right? All the process it will done in sub-basin scale. So here it will done for the each HRU. Okay, it will done for the all 127 HRUs. If you have done that, just click on create HRUs. Click on create HRUs. Just click on create HRUs. Yeah, after creating HRUs, the third step will be highlighted. Edit SWAT inputs. Yeah, edit input and output. Yeah, that is highlighted. Yeah. Step 3 will be highlighted. Highlighted, right? Step 3 is highlighted. Shall I? What happened? But not if you So with this step we have given dem, LULC, soil, slope. Next input is what? Precipitation, right? Precipitation in the HMS we have given only precipitation, but in SWAT we have to give all the weather parameters: precipitation, temperature, solar radiation, relative humidity, wind speed, all those time series data we need to give. Okay. Next step is giving weather parameters.
You can see step 3 is enabled, right? So that is edit inputs and run SWAT. First, we need to connect the databases. We need to connect the databases. So click on connect to databases here. So one pop-up will come like database connection successful. So if you click on connect to databases, that successful message will come.
Database connection successful.
After that, you can go to write input tables. Click on weather stations. So first of all, after the enabling of step 3, we need to click on connect to databases. After successful database connections, we need to go for weather stations. From write input tables are there, no? So from that, you can go to weather stations. In that, the weather generated data, you can give WN user. And then the station count is 4, you can say. You can see the station count is 4. We have only weather parameters of precipitation and maximum and minimum temperature datasets with us. Remaining solar radiation, wind speed, wind direction, and then relative humidity, all will be taken by global datasets. So that this is the option of that thing. So go to weather generated data. You can select second option, WN user. You can say station count as 4 and then click on OK. You can see the process is completed, and then we have already prepared rainfall data and temperature data sets. So we need to import by selecting rainfall data. In rainfall data, we have rain gauges, information from rain gauges. If you check it, the location we need to give here. In rainfall data, we need to select rain gauges. So if you open the directory, we have in weather folder, precipitation means PCP2 folder is there. At last, PCP.txt. PCP.txt. We need to give input. For rainfall data, we need to select rain gauges. In directory, our input files, weather folder is there. In that PCP2 folder is there, subfolder. At last pcp.txt file is there. We need to give that. After given rainfall data, we'll go for temperature. Here, climate stations. We need to check that climate stations. In directory, we go for temperature folder, tmp2. That folder is there. At last, tmp.txt will be there. After giving inputs of precipitation and temperature, we just click on OK. And then click on again OK. Hope all of you completed this input giving.
Yes, sir.
And then you just make sure of that in your laptop or else PCs. So the date should be date, month, year. Not like this, sorry. Month, date, year. Month, date, year. In your PCs or laptops, the date should be in the format of month 08, that is August, 05 date and year. YYYY format. In your PCs or laptops, you just check. It should be in the format of month, date, year. If it is not there, you just readjust that. You can change. You can change like this. Adjust date or time. Date and time. Date and time regional formatting.
Keep in English United States. Don't keep in India, keep in English United States. English United States. English United States. Yeah. English United States. That format was month, day, year. Month, date, year.
Else you can check language as English US.
Okay, 08, 05, 2025. Just change it.
Sir, English India. English United States. It should be English USA.
Yeah.
All of you done up to this? Month, format, date, everything right?
Then click on cancel here. This weather data definition is over for us. And then coming to write input tables, we just click on write SWAT input tables. I already ran this model, so I have completed like in green color. But you need to select all. You need to click on select all. In write input tables, we just go to write SWAT input tables. In write input tables, we just go to write SWAT input tables. In this window, you need to click on select all, and then create tables. It is asking like use weather database to calculate heat tunes for US only, that is for not our Indian case, no. So you just ignore, like no.
Okay, yes, fine.
If you click on S only, okay, but
So here is showing incomplete.
yes, we just select all.
So here is showing incomplete.
Yes, you just select all. You can click on select all, and then create tables.
Yes.
No.
I'm frustrated from this. I asked him, he told me I did
Should be month date.
Do you know my name?
Just to close this thing here, it was not updated. You have changed, keeping open, you are changing, right? Just close it.
You not getting error in the date format and all.
Just close QJS.
Again, start from step 3.
Okay. You are keeping QJS background and you are changing the time, so it is not updating.
No. The first step and second step are done now, so you can start from directly from step 3 onwards. So no need to save them.
So how to open it? Just close the QGIS. You can open it. If you are getting error, then close.
See, for opening the same project, you just click on SWAT icon. You need to select existing project. You need to select existing project. You can give the project where you saved, not new project. You just click on existing project and then you can give wherever you saved. No, you can, yeah.
That too will not take time. That too only takes 1 month. It takes time.
Now go to second step. Change the date. It is not changing. It is there. No splash. Won't be issued splash. So if you are done with this step, you can go and have child.
Some 5 to 10 minutes break.
Sir, you check it and now what is the next step?
Yeah, completed. We just go.
It's completed, come back.
Up to tables creation, right? Right. So we'll go for SWAT run. In SWAT editor, the third option is SWAT simulation. In that, the run SWAT option is there. You can click on run SWAT. Here, our precipitation temperature datasets contains from 2005 to 2008. Jan 1st 2005 to December 31st 2008. Our precipitation and temperature values. So you can select swat.exe version as 64-bit release. 64-bit release. Swat.exe version as 64-bit release. So we are using all 64 bits now. So you can click on 64-bit release. You can check if it is in monthly or yearly or daily. So you click on monthly. And then NY skip is there, number of years skip. You can choose 1 year. Actually, we have 4 years of data. That skip is for warm up period. If you have 30 years, 25 years of data, you can choose warm up period as a 3 years. But we have only 4 years of data, right? So we can choose 1 year as a skip. That is for warm up period. So after that, you can click on setup SWAT run. It will show as finished SWAT setup. And then click on run SWAT. Again, I am saying this process. So we just go for SWAT simulation, run SWAT. You can change the version as 64-bit and skip as 1, number of years skip as 1. You can check monthly time step and click on setup SWAT run. After finished, you click on run SWAT. Hope everyone got SWAT run successful. Okay. Then click on cancel here and we'll go to read SWAT output. Read SWAT output. In SWAT simulation, second option is read SWAT output. In read SWAT output,
Sir, where is it?
so in SWAT simulation, the second option is read SWAT output. In this window, you need to check output.rch, output.sub, output.hru. We need to check 3 here, RCH file, submission file and HRU files. So after that you can click on run SWAT check. Run SWAT check. From that we can have SWAT error checker. if you are up to this SWOT error checker, so just click on examine model output, then it will start the analysis process. If you click on examine model output, it will start the analysis process. And if you click on hydrology here after setup, in this SWOT error checker, if you click on examine model output, it will start the analysis. And then if you go to hydrology, the final water cycle diagram will come like this. So you can observe precipitation value here, average cow number, surface runoff, return flow, lateral flow.
Are you getting this? భయ్యా ఇది కొందరికి రాదులే వదిలేసి ఇది స్వాట్ ఎడిటర్ కొంచెం ప్రాబ్లం ఉంటే రన్ అవుతుంది స్వాట్ చెక్ ఉంటుంది ఇంకోటి అది ఇన్స్టాల్ చేసుకోవాలి రన్ స్వాట్ చెక్ అని ఉంటుంది ఒకటి
ఫైల్ ఏ ఫైల్ అది?
అది గూగుల్లో ఇన్స్టాల్ చేసుకోవాలి సపరేట్గా ఫైల్ ఎవరికి రాలేదా?
ఎవరికి రాదు, చాలా మంది రాదు. Just raise your hands that how many are getting these values and all.
Nobody is getting this, huh?
Only one.
ఫైల్ మిస్ అయింది రన్ స్వాట్ చెక్ అని గూగుల్ టచ్ చేస్తే ఫోల్ డౌన్లోడ్ అయిపోయింది తీసుకెళ్ళి స్వాట్లో పెడితే వచ్చింది బట్ ఇట్ ఇస్ నాట్ ఇంపార్టెంట్ వాళ్ళకి అవుట్పుట్ చూపించు Just I'm trying the Google just go. Okay. Okay, second step we did again. You YouTube are also not getting it. I will thought. It's not coming.
Okay, open channel.
Go to Google. Go to Google. Just type it. Run SWAT check. Just click on this. Download this one. After downloading, just install that software. It is just to show the hydrology of that watershed. It will work. Please install. Now just go to UDA. Just close it. Open it again. Keep it download, but it is not important here. The important one was after importing all these outputs, then just to give some name here to save that.
Simulation 1, SIM 1.
Give it any name. Okay? And then save it. SWAT here, in my case, it is already there. So I am just giving some other name. Click on save simulation. It will save. Then click OK. Save the output. You can plot it. Before installing itself, you just close the QGIS and install it. Otherwise, you will receive error. Whenever you are installing any QGIS things, first close the QGIS and then install. Then you are taking multiple times. It will won't respond. Just write it when it is not coming, just close the QGIS. Save it. Save it. Then run SWAT check. Run SWAT check.
QGS క్లోజ్ చేస్తాను ఇన్స్టాల్ చేస్తాను
some names. This is at what something one. Open it again. చెప్పండి నేను చెప్పండి నాకు చేంజ్ కాదు ఆల్రెడీ సేవ్ చేశాను కదా ఎంతమంది చేశాను అక్కడ నుంచి ఓపెన్ కంప్లీట్ చేయడం ఇంపార్టెంట్ అది కాదు So next step is, so now we have saved the output, right? So we'll go and see the output now. This run swat check, you just install it, close the, before installing close the QGIS, install it and click on run swat check, it will come. Okay, here our important thing is getting stream flow from the map. Okay, basic. So to see the outlet stream flow, just go to scenario, go to your where you have saved the folder, right? Go to that folder, T1 scenarios. Now there is now there is no need to worry about QGIS. Now we have already saved the output. Just close it. If it is not responding, also don't worry.
In your practice file, we have scenario, source, and watershed, something like that. We can click on scenarios. For our case, 3 are there, but your case maybe 2 are only one. So in that,
What help you this once you explain
So now we can see the values. So in your simulation file, we have 3 subfiles right. We need to select text in out, txt in out out. In that folder, we need to search output.std. Output.std file. We need to search. In scenarios, in simulation folder, we have text in out folder. In that, we need to search output.std file. Output.std file. We need to open that. If you open, you can see our SWAT version and all, and then so annual summary we can see, like what is the precipitation, surface runoff, lateral cube, so lateral runoff, and then groundwater runoff. We can see here in monthly time step. For the first year, we can see 12 months here, and then 2006 here, 2007, 2008. We can see, and then annual average value also we can see here. So overall precipitation is like this: snowfall, snowmelt, and then groundwater, total aquifer recharge. All of you can observe here. Hope all of you are able to open this file.
Can you repeat it?
Yes. Wherever you practice now, open that directory. In that, in your simulation folder, we have 3 subfolders. In that, text in out folder is there. text in out, text in out. We need to search output.std file. Output.std file. This one. std file. .std file. std. Output.std file is there. You need to search and then open it. We can see the simulated values of major components of hydrology like precipitation, surface runoff, lateral runoff, groundwater recharge and all, and water yield, sediment yield and all. And the annual average value is also visible here in this file. We can check what is the precipitation.
So SWAT will give you so many outputs, not like only stream flow. It will also give you how much groundwater is there, what is the soil moisture, what is the sediment. So all those outputs are there.
Yeah, just open.
Just see the output. What are the variables it is giving? Just see the full output. It will give you time series data for each and every month. What is the value? If you see this output, you will get all the values for each and every subbasin. So we have 5 subbasins, right? So till 5 subbasins 005. So till 5 subbasins you will get the results separate. Okay, like you will also get dot SUB means subbasin parameters. Dot SOL means soil parameters. Dot MGT means management parameters. Like who are looking for agriculture purpose, they look into MGT. So there are different options. Dot GW means groundwater parameters. Dot RT, dot SCP, so many things are there. All are for different purposes.
So I think all of you got this, right? Can we go for slack cup calibration part?
So the out you see the where the outlet, like what is the subbasin and subbasin of outlet. So I think our outlet was here, right? The left corner, which is falling in first subbasin, right? So there you have to extract your stream flow data, okay? Then you compare that with the observed data, whatever you have given already, observed data, and compare those two with some metrics R square and NSE, like how we did in HMS. In that it will automatically throw you NSE, right? Here you have to perform outside, find out R square NSE and see how the flow is there. Is it able to predict the observed flow or not? If it is not, then we have to do calibration, right? And then you are getting that point?
So only R, NSA and R square.
There are so many metrics, but NSE is better. If you see only R square will give you only linear relationship between X and Y in simulated with the observed. For example, if the observed flow is increasing, the simulated flow is also increasing, means it will give you the good correlation. But for example, the value in the observed flow is 50, but value in the simulated flow might be 20, but it is having 30 difference. So when you check that NSE, it will also check the bias between two. If that is close, then NSE will come good. Yeah, it will check with all the points. If all the points are having less bias, then your NSE will come good. Yeah, but R square will give you only the pattern. It will is it following with the observed pattern or not? If it is following with the observed pattern, R square will be good. But that accuracy also it maintains, then NSE will be coming good.
So if we want to see furthermore, what are the parameters that are needed to be considered along with NSE and R square?
Now, it depends. Like if you are focusing on peaks,
like RMSE.
If you are focusing on flood studies, you have to check the peak differences that you will get through P bias or RMSE, all those indices. If you are focusing on stream flow for water resource management, so then you have to check NSE, so it will give you for the entire time series. So it depends on our work. There are so many metrics. So after getting output from here, you have to compare with observed data, then check it is able to predict or not. If it is not, then we have to do calibration. Nothing but we have to, whatever the model estimated parameters with our given data was not able to find the observed flow, right? It was not closely matching with the observed flow. So we need to adjust those parameters.
Ultimately, the deviation should be as minimum as possible.
Yes. So to adjust those parameters, we need to optimize it. So in the HMS, it is already inbuilt. So we directly optimize it in the HMS itself. But in the SWAT, we have this we can do in anywhere. Like if you have a optimization algorithm, you can do it separately also. But SWAT people also developed this SWAT cup for doing calibration. Okay, for doing calibration. So for that, understood, right? Why we are going for SWAT cup? For calibrating the parameters. That we have to do until we get best match with the observed data. So for the SWAT cup model, what will be the input? Whatever the output which is coming from the SWAT, it will be the input for the SWAT cup. So open SWAT cup. Sure, SWAT cup.
So we'll go for SWAT cup. Just open SWAT cup software, please.
Actually, we are not checking that R square NSE. You can check how it is predicting. Obviously, it will be less only. So you have to go for calibration. But to get the clarity, is that peaks are matching, either our flow is over predicting, under predicting, it is always better to draw the hydrograph, then see how to change the parameters based on that. Open SWAT cup. Open SWAT cup.
I think all of you opened SWAT cup software.
Open SWAT cup. First
Now,
step was
you go to start here, click here to start now. Just go to start. Click on new. And this wizard will come. And then click on next.
here.
Here, one text in out location we need to give.
We got text out folder, right? So that text out is the input for the model. Yeah, better save it in the same SWAT, wherever you have saved SWAT. TV1 scenarios, simple.
So you can go up to text in out file. In scenarios, one text in out file is there. That is not in inputs, that is in our saved SWAT simulation there now. Wherever we practiced it.
It will that pink file. Text out. Select that. Select the pink file. Click on open. Click on open. Then click next. After that, choose version.
Version is SWAT 2012, I think.
Yeah, 2012.
And then bit is 64 bit.
I think all of your laptop are 64 bit on it.
SWAT version is 2012 and the processor is 64 bit and the optimization algorithm is SUFI2.
There are so many algorithms. These are optimization algorithms for doing calibration. The SUFI2 is one of the, like, out of all the 5, SUFI2 is better for stream flow
Prediction.
Purpose. So we are going with SUFI2.
And then we can give the name as SWAT Cup Trial 1.
SUFI2 full name is Sequential Uncertainty Fitting Algorithm.
And then you need to give the directory for project location also. After that you just click on finish.
Project location you give the same.
In the left side you can see the calibration inputs, executable files, calibration outputs, sensitivity analysis and all.
సార్ మినిమం ఎంత వస్తే మన మోడల్ మంచి పర్ఫార్మెన్స్ ఆ టైంలో నాకు కాంప్రమైజ్ కావాలంటే ఎంత పాయింట్ వస్తే ఓకే అంటే ఓకే అనుకోవచ్చు. ఎంత కాంప్రమైజ్ అయిపోతుంది 7
Project name, project location. All of you reach here. Just click on this top 3 are there now. Just click on reach. Click on reach. So open this calibration inputs. The first thing what we need to do is click on this parameter info text, information text. So here, whatever the parameter you want to optimize, all those parameters you should mention here. Okay? There are so many parameters, right, to convert precipitation to runoff. So all those parameters you can optimize. She's doing something else.
So here the default parameters are 4. We'll go with these parameters only now. Yeah. So we need to change the simulations. Number of simulations as 5.
First we'll try with 5.
Now we'll try 5 only, otherwise it will take 1 more hour. So number of simulations as 5. Yes. The default parameters are 4. So number of simulations are 5. And then coming to this Sufi12 swat edit.df. So the starting simulation number is 1 and the ending simulation number is 5. We change now 5. We need to skip the file.save file. We don't need to change anything here. And then that absolute values also, we don't need to change anything here. And in observation, we need to change here only. So in observation, you need to select RCH, reach files. Selected? Right. In that, observe.rch.txt is there now. Here we need to change. Just open the input files. In that swatcup.xls is there now. Just open swatcup. This. In swatcup Excel file, actually we simulated from 2005, right? But we have warm-up period as 1 year. So we don't need to give the first 1 year data. So we will start from 2006. So 3 years data we need to give there. In this file, we have 3 years, right? 36 months of data is there. We just copy those things. 3 columns, one serial number and flow, and then the stream flow value. We just copy these 3 columns. Coming to here, we just replace them. All 36 values we just replace here. And then you need to change the number of data points as 36. Number of data points as 36, and we need to change the values in the now. Yes, till down. Yes, all the values you need to remove, and then you need to paste for only 36 values. Whatever the values are there, we just remove that. You just copy only 36 values, and the number we need to change as 36 number of data points. And we are targeting as
Okay, you can just paste it also. It will take, it will just feed for
and
36 rows.
we are targeting only stream flow, right? We are preparing the data sets for stream flow now. So we need to change number of variables as 1.
As we are focusing on only stream flow, so that only one variable, keep 1.
We are simulating only stream flow values here. So we just keep the number of variables as 1. And our data points are 36, and we are pasting here. And then you come to this RCH and HRU is there now. You just click on HRU. To see files are there or not, that's all. And then we need to change one more time at objective function. Observe.txt here is there. You need to again change here. You need to change 36 number of data points. Yes.
Observe reach reaching sir.
First, we will go to observation. In that observed rch.txt, we need to change number of observed variables as 1, as we are targeting only streamflow simulation. So one variable we are targeting, and then our number of data points as 36, and then we are copying these 36 values here, and we need to paste here. Whatever is there in previous, we need just remove. After completion of this step, we just go to objective function. In the objective function, we have observe.txt file is there. In that again, we will start from number of observed variables as 1. And then our number of data points is 36, and we will remove all the values here and copy these values and paste here. In this objective function tab, we are editing observe.txt file. In that we are changing number of observed variables as 1, and then number of data points as 36, and we are copying the flow data here. Hope everyone completed this time. And then after the observe.txt file, we have variable file name.txt in objective function tab. So we just remove remaining clouds. In SWAT, we have observed that our outlet is at first basin. Whether you observed or not, I don't know, but we have 5 subbasins, right, in that watershed. We have the outlet at first subbasin. So flow 1 means our outlet subbasin, that is. So we have only one outlet in our study area, so that we need to do for one thing. And after RCH, after HRU, we have subbasins. We need to click here, subbasin, and then the observed sub.txt file will open. Just for checking only, no need of doing any editing here. And we'll go for extraction. Our observation is complete. Our objective function also completed, and then we'll go for extraction. Here also we'll remove the other 3 outlet subbasins we'll keep only one subbasin as float1.txt. In extraction, first one is variable file.rch.txt file is there. Just open. We have 4 or 5 files are there, but we need to keep only one. Float1.txt. Yes. And directly you can go to sufi12 extract.rch.def. Directly you can go for sufi12 extract.rch.def file. In this, we can change here the beginning year of simulation, which is not included in the warm-up period. So we can give as a 2006, not 5, because the warm-up period we have put now 1 year. So, and the end year of simulation is 2008. And you need to delete these 2 rows. You need to delete the 2 rows above the beginning year of simulation. We just delete. And we need to change here number of variables to get. We are targeting only stream flow. So only one. So that stream flow values in column number 7. So we can delete 18. Only one variable, that is 1 stream flow. The stream flow is corresponding at 7th column. Right. So total number of subbasins are 5 in our case. So we need to change total number of subbasins as 5. So number of subbasins to get for the first variable as 1 only. 1. Subbasin number also 1. Our time step is monthly, so 2. So yes, change according to this 1, 7, 5, 11, 2006, 2008 and 2.
Just check all the changes are done or not. If anything is not done, it will throw error.
And then after that you can click on save all. Save all. You need to click on save all. All of you completed, right? I think. Yes. First,
just see here.
Coming to calibration inputs.
Just cross check with your things.
First one, parameter info.txt. In that we have 4 parameters. The number of simulations as 5. And then the starting simulation and ending simulation numbers will be changed according to that 1 and 5. We don't need to change file.cavo and absolute swag values also. Right. Coming to observed rch.txt in observation wizard. So we have number of observed variables as 1 and we have 36 data points. We removed the earlier ones and we pasted the new float files here, float values here. No need of change here in observation. And coming to extraction, we need to remove all other float files. Only float 1 is there. No need here. In this is an important thing. We need to edit. In output.rch, one number of variable as 1 and the column number is 7 and total number of subbasins as 5 and number of subbasins to get the first variable as 1 and the number of first variable reach of the variable is 1 and beginning year of the simulation is 2006 and end year of simulation is 2008 and our time step is monthly. Yes, I think we are going to objective function. In objective function also we need to change the observed.txt. Here number of observed variables as 1, number of data points as 36. We need to change the data here and variable file name.txt as float1 and we need to save all. After that, this calibrate option is enabled.
It is not enabled for some of them.
Some of them it is not enabled, right? For that, we have shared one file like
In the input,
in input files. swag 2012.exe is there. You need to copy this to in C drive, in swag editor. You need to paste here that swag 2012.exe. Yes, it is already there.
yeah, you replace it.
Just replace, yeah.
Replace it.
In C drive, we have folder called swag. In that swag editor is there. In C drive, swag editor will be there.
See swag.
We are seeing that only. Yeah. Swag to the just
See swag.
whatever we gave now in input files, swag 2012.exe. You need to copy there and you need to paste here. Not this file to there. Input file is there, no? No. So actually that we shared the morning input files. In that you are using that swag cup, or yesterday you installed that swag cup from website?
Yesterday.
Okay. Actually, so we forgot to mention that no, that is not that is licensed one. Yesterday's from website. We are giving actually morning no. So that is the free version actually.
Ishwar, we'll tell that and we'll show here. I'm ready.
All the items. We need to give command as Y.
Yes, clicking yes.
And then the execution will start here.
Like that, it will do up to 5 simulations.
And we need to start the post back. So the calibration is done. We can save our iteration. We can see the iteration history here. We can see the summary here. See, our R square value is 0.94, which is 94% is accurate, and then NSE also 90% is efficient. So our uncertainty plot for observed and simulated values is like this. So only 36 values are there now. The blue one is our observed values, and then the red one is simulated values of stream flows. So our model is very good simulated.
Actually, it is only 3 years data. That's why the performance was good. If it is a long term data, then the performance will vary. That time, this calibration will be helpful. Now we have nothing did. Just whatever the default parameters are there, that only we updated. We went with only 5 simulations. That's why it is not much changed. But the 3 years data, whatever we are getting, it was compared to, like, it was very good with observed data. That's why the performance metrics are coming good.
Parameters అనేది సెన్సర్స్ యూజ్ చేసి డేటా తీసుకుంటుంది సార్ వేరియబుల్స్ ఆ డేటా తీసుకుంటాం సో ఐ వాస్ పర్సెంటేజ్ తెలుసుకుంటే ఈజీగా వస్తుంది డెమో కూడా మంచి ఫైనల్ వస్తుంది ఇదంటే స్క్వేర్ కిలోమీటర్ ఏరియా ఆర్గనైజర్ మనకుంటే జస్ట్ 30 స్క్వేర్ కిలోమీటర్స్ అప్పుడు ఇదంటే మనకి డెమో కూడా హై రిజల్యూషన్ డెమో ఉంటాయి We are giving only 4 parameters. So if you give 12 parameters, and simulations also we gave us only 5. It will go more simulations, right? So maximum NDS data NDS and one system capacity one దగ్గర 512 GB RAM ఉంది 20 years data
Sir,
actually the file we shared now for SWAT cup, it is not correct, that licensed one. We'll again share to you, just practice. This is, I think, simple steps only, calibration. You can check it home actually.
anyone having any confusion? Anyone having any confusion? whatever we are using, like March and whatever we are, that is correct. That is showing that.
रन होके सेव हो गया बार बार रन कर रहा था ना क्यों नहीं रहा मैंने तुझे एक बार डायरेक्ट उसके बाद क्या
Sir, Anna, I'll just complete it.
So actually, you need to go Homi Baba Seminar Hall complex. So we'll move forward now. Yes, starting.
It's 5 to 6 now.
It's just 30 minutes session only. You just go there and again, sir. So please, we'll move forward to Homi Baba Hall. That is Seminar Hall complex, ground floor. Yeah, we'll close here. We'll send the correct file or actual version. Yeah. PPT also I will share. Yeah.
Instead of downloading whatever we are using, that we will share.